Good morning, everyone. We welcome you all to the International Seminar on Advanced Materials, where we explore the innovations that are shaping our future. Just last week, we had the privilege of witnessing a rare astronomical event, a perfect planetary alignment where Venus, Mars, Jupiter, Saturn, Uranus and Neptune appeared in a straight line. This rare cosmic order reminds us that in science, everything is interconnected, just like the materials that build our world. Before we begin, let us invoke the blessings of the Almighty with a prayer song and followed by Tamil Thai Valthu. Check 1, 2, 3. Hello. Hello, check. Hello, check 1, 2, 3. Check 1, 2, 3. Hello. Hello, check. Thank you, sir, for your warm words of welcome. Science and innovations are about pushing boundaries. Just recently, SpaceX achieved the impossible, catching a rocket booster mid-air using giant mechanical arm. This game-changing moment in spaceflight reminds us that even the most ambitious dreams in material science can become reality with determination and precision. As we explore these advancements, it's my privilege to invite Reverend Dr. Paul Raj, the Rector, to enlighten us with the words. Thank you, Father, for your kind words. Sometimes revolutionary discoveries come from a simple experiments. Two physicists discovered graphene, one of the world's strongest and thinnest materials, using nothing but a pencil and Scottish tape. It later won them the Nobel Prize and is now transforming nanotechnology. I invite Reverend Dr. Maria Das, our principal, to share his reflections. Here, we not only celebrate the start of an intellectual journey, but also mark the formal release of a significant academic contribution, the conference proceedings. This compilation is a reflection of the dedication, hard work, and research excellence of scholars and experts in the field. First MSc girl students kindly occupy the seats from the front. First MSc students, girl students, kindly occupy the seats in the front, including sister. Students, kindly come front. Instruction by professors. Sir, கேட்க மாட்டேங்கிறேன். Check. Check 1, 2, 3. Check. Check, check, check. Check 1, 2, 3. Check.
Students, kindly maintain silence. Possibly will be starting. The dignitary is walking to the dais.
Students, kindly maintain silence. The dignitaries are on the way. Good morning, everyone. It is an honor to welcome you all to the International Seminar on Advanced Material, where we explore innovations that are shaping our future. Just last week, we had the privilege of witnessing a rare astronomical event, a perfect planetary alignment where Venus, Mars, Jupiter, Saturn, Uranus, and Neptune appeared in a straight line. This rare cosmic order reminds us that in science, everything is interconnected, just like the materials that build our world. Before we begin, let us invoke the blessings of the Almighty with a prayer song and followed by Tamil Thai Valthu. I kindly request everyone to rise.
Bless the Lord, oh my soul, worship His holy name. Sing like never before, oh my soul, I'll worship Your holy name. The sun comes up, it's a new day dawning. It's time to sing your song again. Whatever may pass and whatever lies before me, let me be singing when the evening comes. Bless the Lord, oh my soul, worship His holy name. Sing like never before, oh my soul, I'll worship Your holy name. I'll worship Your holy name. நீராறும் கடலுடுத்த நிலமடந்த கெழிலொழுகும் சீராரும் வதனமென திகழ் பரத கண்டமிதில் தெக்கணமும் அதிசிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை நுதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம் வியந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
Thank you, students, for your prayer song and Tamil anthem. Every great discovery starts with curiosity. Take Isaac Newton, for example. When an apple fell from a tree, he didn't just pick it up. He questioned why it always fell downward, leading to his theory of gravity. Like Newton, today we gather here to question, explore, and push the boundaries of material science. To formally welcome this distinguished gathering, I invite Dr. I. Johnson, the convener of ICAM 2025 and head of Department of Physics, to deliver the welcome address.
A very good morning to all. In order to govern, the question is not to follow out a more or less valid theory, but to build with whatever materials are at hand. In the inevitable must be accepted and turned to advantage, said by the famous Napoleon Bonaparte. So we are living in a world which is nothing but a materialistic world. Material science is an interdisciplinary field that examines the properties, structures, and applications of various materials, integrating principles from physics, chemistry, and engineering. Its evolution is deeply intertwined with human history, as advancements in material usage have often defined technological progress. From the ancient mankind onwards, தமிழில் சொல்லுவாங்க கல் தோன்றி மண் தோன்றா காலத்துக்கு முன் தோன்றிய மூத்த குடி அப்படின்வாங்க. From such an ancient time onwards, the mankind came through different ages: Stone Age, Bronze Age, Iron Age, Nuclear Age, Nano Age, and Silicon Age. So these are the various ages through which the mankind revolutionized itself in the materialistic world and finds applications of various type of applications because of the materials advancement. And we are living in an era where we are having wonderful materials which are used for many fold applications. We can take one material which can be used for a number of applications. We can tailor the property of the materials. What type of applications we want, depending on the applications, we can develop the new materials. So such a powerful materialistic world is existing all over the world today. Whether it is pharma industry or bio industry or solar industry or wind industry or defense industry or health care industry, whatever may be the industry, or agricultural industry, whatever may be the industry, these materials are playing a major role today. The Indian government understood the concept of a semiconductor industrial revolution and started a good initiative in Delhi and Chennai and by bombing semiconductor parks. I hope that this material revolution will take India to a greater height in the international arena. In that aspect, last year we conducted International Conference on Advanced Materials 2023, which has been chaired by the DRDO DMRL Director and also funded by CSIR and DRDO. I am happy to inform you that today's conference has been funded by CSIR and TNST. And not only that, it has been chaired by Professor Armugam, the Honorable Vice Chancellor of Tamil Nadu Open University. I welcome you, sir, on behalf of our beloved management. So Dr. Armugam is an eminent scientist, and he usually called as a foreign scientist by Bharatiyasan University professors. Whenever we used to go to the Bharatiyasan University those days, his room will be locked and people, neighboring professors. Well, there was one group of professor. For me, Dr. Ramamurthy, he used to tell, how can you come here to find Armugam? Armugam will be in Japan, Taiwan, or France. Like that, he used to make a joke with me, Dr. Ramamurthy, the former head of the Department of Physics at Bharatiyasan University. So such a kind of caliber with Dr. Armugam, and it is very fortunate to have him in our midst for this international conference. We are having more than 76 papers accepted for this conference, and we hopeful of publishing the papers in Scopus or Web of Science indexed journals. It's my pleasant duty to welcome our Reverend Father Rector, who is a gold medalist from the chemistry department of our St. Joseph's College. Father is not only in the religious field in those days, but also in the academic arena. Father was a renowned international religious speaker and preacher all over the world and lived for more than a decade in the European countries. So I welcome Father on behalf of all of you. We are having a eminent and enthusiastic personality. He used to always, be, whenever I write a email to some of my foreign scientists, and one person used to respond to me, cheers in Christ. His name is Christ, that professor name. from Belgium. He used to write me, cheers in Christ. So we are having a cheers in Amal, like that. Father Amal, who is always cheering us, and I welcome you, Father, on behalf of the business department. Our beloved Reverend Father, Principal Dr. Mariadas, is a eminent personality, a versatile speaker, and also a very subject-oriented person. See, he is very objective in his approach, and especially he used to have many wonderful initiatives in the academic arena. His interest thrives the department, and each day we used to get suggestions from him for the betterment of the department. He used to always lend a source of great help for the student development. He is a student-centric person. I welcome you, Father, on behalf of the department. So I welcome many international scientists who will be joining later today and also tomorrow by either by offline or online all over the world, across the globe. Almost we are having representation from all continents through online as well as offline. So I welcome all of them on behalf of the department, and I welcome my beloved staff, both teaching and non-teaching, and the student fraternity. And the students are the most important people who are going to be benefited because of this conference. Not only students from St. Joseph's, all over India, people are watching this conference by online, researchers, faculties from Rajasthan, Uttar Pradesh, Madhya Pradesh, New Delhi. So people are online. I welcome all of them on behalf of the Department of Physics, St. Joseph's College. Welcome one and all.
Thank you, sir, for your warm words of welcome. Science and innovation are about pushing boundaries. Just recently, SpaceX achieved the impossible, catching a rocket booster mid-air using a giant mechanical arm. This game-changing movement in spaceflight reminds us that even the most ambitious dreams in material science can become reality with determination and precision. As we explore this advancement, it is my privilege to invite Reverend Dr. Paul Raj, the Rector, to enlighten us with his words.
Dear Father Secretary, Father Principal, the chief guest of today, Dr. Arumugham, the Dean Charles, the head of the department Johnson, the organizing secretaries, heads of the departments from other faculties, students from St. Joseph's College and other colleges offline and online. I am delighted to be here in a very, very important international conference on advanced materials. I don't know whether you people read the famous novel by Paulo Coelho. Have you heard about this name at least? Great, thank you. Paulo Coelho wrote a very famous novel called The Alchemist. In that, a person is in search of the alchemist, and he himself becomes the alchemist. Do you know who is an alchemist? Alchemist is the one who will change any material into gold. Because at that time, gold was the advanced material. Any material, he has the capacity to transform that material into gold. My dear friends, advanced material is a new era in the science as well as in the research arena, calling us to move from one step to another step, making use of the materials for the good of humanity. This seminar, in the presence of Dr. Arumugham and his insights, will enlighten us to move further in this special area of advanced materials. And I wish you all the best. God bless you all.
Thank you, Father, for your insightful words. It's incredible how accidents in science have led to some of the greatest discoveries. Did you know that safety glass used in car windshields and bulletproof windows was discovered when a chemist accidentally knocked over a beaker coated with cellulose nitrate? Instead of shattering, it held together. A true example of how science works in mysterious ways. With that said, now I'm delighted to invite our Reverend Father Secretary Dr. K. Amal to share his insights and felicitate this gathering.
Respected Father Rector, Father Principal, the head of the department, staff on the dais, and members sitting in the aula, my dear beloved students from other parts of the colleges here. I join all of you in welcoming Dr. Arumugham, a really versatile personality in the field of science, who has produced enormous research publications of world standard. We are privileged to have you, sir. The topic is so relevant today, advanced materials, International Conference on Advanced Materials organized by our Department of Physics and is sponsored by Council of Scientific and Industrial Research as well as the Ministry of Science and Technology, the Government of India. I think it is a great honor given to our college that these two important institutions supporting us. Certainly, with all your commitment and hard work down the few months you have been working at it, certainly it's going to be a great success. There is no doubt about it. Thank you, sir, for introducing me as Cheer Amal, not Beer Amal. The way he was welcoming everyone, I was a bit worried. In a modern world like this, as we are moving the world of engineering and modern science, these advanced materials bound to revolutionize many developments and growth of our world. And nanomaterials, you know, it's one of the subsets of these materials, advanced materials, which is bringing about huge change in the use of advanced materials. And it is a life-changing revolution as it is. Every field, as it was mentioned by your HOD, any field you mention, you have advanced materials, nanomaterials playing a very vital role. And it touches all of us, everyone's life, and the life of the nations and the world. It is also, I'm sure this 2 days conference certainly will bring about a new focus on critical issues, areas such as advancing next generation medical diagnostic technologies, developing integrated devices to combat cardiovascular diseases, energy disease devices, advanced material characterization techniques, applications in renewable energy, and supercapacitors. This is such a diverse application. You are all aware of it in the field of aerospace and defense, sensor, flexible displays, healthcare, solar cells, etc., etc. My dear friends, this is for the young minds, like you students, young research scholars. Such a volume of research complexity of things which we need, the world is trying to match up its requirements, it is bound to create side effects, challenges. And it is also, we are also heading towards dangerous trend in terms of putting the entire earth at risk, the entire universe at a risk in a way, like a huge volume of warmth in the world and the heat that is being produced. Those things we need to take into consideration. The humans are important, as well as the universe is also equally important, the nature. And how far this revolutionizing advanced materials, how far it is going to affect these two factors is a real challenge before the young mind. You need to find out a solution to it. Otherwise, we will be annihilated. There won't be any humans to live and to find out to enjoy all these cherishable findings, produce or products, whatever it is. Therefore, my dear students, with this challenge before you, let us get into the research. Let us get into our own life cycle as an analysis part of it. And in this context, the collaboration between the researchers, academicians, as well as industries are very crucial and important. I suppose these 2 days conference will highlight all these critical issues and challenges before you, particularly the young minds, because you are going to be our future. You are going to bring about huge change in the world. With these few words, I congratulate the entire department, particularly the HOD and Dr. Maggie and all others who are behind in organizing this wonderful 2-day conference. All the best and God bless you in all your endeavors. Thank you.
Thank you, Father, for your kind and encouraging words. Sometimes revolutionary discoveries come from simple experiments. 2 physicists discovered graphene, one of the world's strongest and thinnest material, using nothing but a pencil and a Scottish tape. It later won them the Nobel Prize and is now transforming nanotechnology. I invite Reverend Dr. Mariadas S.J., our principal, to share his reflections.
Respected Reverend Father Paul Raj Michael, our rector, respected Reverend Father K. Amal, our secretary, Dr. Johnson, the head of the department, Professor S. R. Mugham, Vice Chancellor, Tamil Nadu Open University, Chennai, today's chief guest, Dr. E. Maggie Diana, Dr. Charles, Dean of Physiological Science, respected professors and my dear participants, good morning to you all. First of all, I would like to appreciate the head of the department, all the staff members for organizing this wonderful seminar on advanced materials. I don't know about these advanced materials because I belong to commerce team. When I read the title advanced materials, all that came to my mind was materials in progress in commerce term. Materials we know, in the account balance sheet or let's say accounts you will find materials, raw materials and raw materials in progress, something like this. That's what came to my mind. However, you know very well what is the meaning of these advanced materials. Before I speak something on the topic, I would like to know how many participants are from other institutions. Please stand up. Apart from St. Joseph, how many are? Anybody sitting here? All the others are online. Okay, now may I invite all the Josephites to put your hands together and welcome all the non-Josephites. Thank you, please sit down. I was going through the topic, these advanced materials, what it can mean. Then it says here are some examples like nanomaterials, smart materials, energy storage materials, biomaterials, metamaterials, ceramics and glass, polymers and composites, quantum materials. I don't know anything about of this topic. But you know, but at the end, towards the end it says, these advanced materials have the potential to transform various industries, including energy and environment, healthcare and medicine, aerospace and defense, electronics and communication. So these advanced materials are spread over in all the aspects or let us say factors of our life. That's what I understand from this. Whether it is health, whether it is intelligence, even whether it is a spiritual aspect of our life, definitely this advanced aspect is very, very important. Whom do we say that so-and-so is very advanced? What does it mean by that? That particular word advanced, that invites, I think, all of us to think how far we are advanced in our thinking aspect, how far we are advanced in our approach, in our relationship. This word advanced means, in my opinion, crossing the borders or going beyond. Only when we go beyond, whether it is your academic life or professional life or personal life, only when you are advanced, the society will respect you. People will say, so it is advanced because in terms of knowledge he is advanced. When people say that so it is advanced, in terms of relationship, the person crosses the boundaries. It doesn't mean, let us say, he doesn't confine himself any to caste, any color, any creed, or doesn't have any borders. He thinks beyond, his feelings are beyond, and he goes beyond, and he does beyond. Only then the society will respect you. And this particular topic, in my opinion, is inviting all of you to go beyond in your intellectual capacity. Whether it is research scholars or UG or first year or third year or first PG, doesn't matter. But these topics, of course, you will discuss it differently on these topics, but I thought all of us need to go beyond, thinking out of box, crossing the borders. Only when we go beyond, we are telling the society that we have something to contribute to the society, whether it is at the intellectual level or at the personal level. Even in terms of, you take our own institution, there are persons who are thinking beyond, who are willing beyond, who are doing beyond. That's why they remain in the campus for a long time for carrying out any academic activity. Therefore, my dear participants, let us take a kind of resolution that we will go beyond. We will cross the boundaries. We will think beyond so that the society will learn from something, and all the persons, those who are respected, whether at the social level or intellectual level or spiritual level, all those persons have beyond themselves. They have thought beyond themselves. தன்னை கடந்து சிந்தித்தவர்களாக பார்க்கிறோம். எப்பொழுதெல்லாம் தன்னை கடந்து யாரெல்லாம் சிந்திக்கிறார்களோ அப்பொழுதுதான் அவர்கள் இந்த சமூகத்திற்கு ஒரு எடுத்துக்காட்டாக, ஒரு செய்தியாக, ஒரு முன்மாதிரியாக இருக்கிறார்கள். இது போன்ற அமர்வுகள் எல்லாம் உங்களை கடந்து சிந்திக்க அழைக்க வேண்டும். அதுதான் இந்த நாளிலே நமது சிறப்பு விருந்தினராக இருக்கலாம், அல்லது இன்றும் நாளை நடைபெறவிருக்கின்ற அனைத்து நிகழ்வாக இருக்கலாம். உங்களை கடந்து எவ்வாறு சிந்திக்கிறீர்கள், உங்களை கடந்து எவ்வாறு வாழ்ந்து கொண்டிருக்கிறீர்கள், how you are thinking beyond, how you are feeling beyond, how you are speaking beyond, how you are crossing the borders. Only then the society will have something from you. The society will respect you because you become somebody in the society. If you are respecting today Dr. APJ Abdul Kalam, that he is our alumnus of this department, it is because he has contributed something very important to the society by going out of himself, by thinking out of the box. Therefore, my dear participants, please allow your mind to examine whatever is going to happen, personalize whatever is going to happen, then the society will learn from you, and that's why the department is taking lots of efforts to organize such workshops and other conferences. I'm sure you will make use of the wonderful opportunity, God-given opportunity, I would say, and I would like to appreciate and thank and express my sincere gratitude all the supporting agencies for conducting these conferences. Thank you very much. May God bless all your efforts.
Thank you, Father, for your inspirational words. Last year, the James Webb Space Telescope stunned the world by capturing the deepest images of our universe. It showed us exoplanets, distant galaxies, and even the first light after the Big Bang. Did you know that none of this would be possible without ultra-thin, heat-resistant materials, which is coming under the advanced material category, developed for its mirrors and sunshield? With that said, it is time to honor. Today, we honor a visionary in material science whose work, like Webb's mirrors, helps us see beyond limits. I now request Reverend Father Rector to adorn our esteemed Chief Guest, Professor S. R. Muham, Vice Chancellor, with a shawl. Followed by that, I request Reverend Father Secretary to present the memento to our Chief Guest. And I invite Reverend Father Principal to offer a book to our Chief Guest. Now I request Dr. I. Johnson, the convener, to honor Reverend Dr. Paul Raj Michael, the rector, to honor with a book. And I also request Professor Patrick Prabhu, the co-convener of Physics Department, to honor Reverend Dr. Amal, the secretary, to honor him with a book. I request Dr. Maggie Diana, the organizing secretary, to honor our beloved principal, Dr. Mariadas SJ, with a book. Once again, I welcome Dr. Maggie Diana to honor our Dean of Physical Sciences, Dr. J. Charles, to honor him with a book.
Thank you all. Here, we not only celebrate the start of the intellectual journey, but also mark the formal release of significant academic contribution, the conference proceedings. This compilation is a reflection of the dedication, hard work, and research excellence of scholars and experts in the field. It serves as a valuable reference for future studies and innovation in material science. To officially unveil the conference proceedings, I invite our esteemed dignitaries to join on the stage. Professor S. Arumugam will unveil the conference proceedings, and the rector will receive the first copy of the conference proceedings. With this, we officially commence the International Conference on Advanced Materials. May these proceedings inspire groundbreaking discussions and collaboration in the field of advanced materials. Thank you all.
A great scientist once said, research is seeing what everybody else has seen and thinking what nobody else has thought. With that said, I invite our distinguished chief guest, Professor S. Armuham, Vice Chancellor, to enlighten us with his address. Welcome you, sir.
அனைவருக்கும் வணக்கம். Respected Rector, Reverend Dr. Paul Raj Michael, Principal Reverend Dr. S. Mariadas, and other dignitaries in the dais, faculty members of Physics Department, and also faculties from other universities and colleges, and the organizer Dr. Johnson and other students and friends. Good morning to one and all. It gives me an immense pleasure and honor to be a part of International Conference on Advanced Materials, ICAM 2025, organized by the illustrious Department of Physics, St. Joseph College, Tiruchirappalli. At the outset, let me express my heartfelt gratitude to the organizers for inviting me as chief guest for this significant academic event. St. Joseph College stands as a beacon of excellence in higher education with its long-standing legacy of imparting knowledge, producing leaders, and shaping futures. This institution, with its glorious heritage spanning over 180 years, has carved a niche for itself not only in Tamil Nadu but also in the global stage. The remarkable achievements of its alumni, including luminaries like Dr. APJ Abdul Kalam and Dr. G.N. Ramachandran, exemplify the transformative power of this college mission for the good and the true. Today, as we convene to discuss advanced materials and their applications, we are not just participating in academic exercise, but in a journey that addresses some of the most pressing challenges and opportunities of our lives, of our times. Material science is a foundation upon which modern technology rests, from the nanomaterials that power our smartphones to superconductors, revolutionizing the energy transmission, from bio nanomaterials, enhancing the medical application, to sustainable energy solutions. This field influences every sphere of human life. The scope of this conference, encompassing nanomaterials, energy storage, bio nanomaterials, environmental impacts, and modeling, showcases the multidisciplinary nature of this field. The conference also underscores the necessity of collaboration across disciplines, institutions, and even countries to tackle the grand challenges of the future. Take, for example, the role of nanotechnology in healthcare. The development of biosensors and nanodrug delivery systems is transforming the way diseases are diagnosed and treated. In the energy sector, materials designed for supercapacitors and hydrogen evolution reactions are paving the way for sustainable future. Such a breakthroughs highlight the central role of material science in shaping a smarter, greener, and more equitable world. India, with a strong research institution and growing emphasis on innovation, has emerged a key player in advanced materials research. Government initiatives like Make in India and National Mission on Quantum Technologies and Applications are creating opportunities for translating materials research into industrial and societal applications. St. Joseph College, with its research-driven ethos, is contributing meaningfully to this national mission by organizing conferences like ICAM 2025. The institution is not only fostering a culture of inquiry but also inspiring students and researchers to push the boundaries of what is possible. One of the primary objectives of this conference is to create a platform for knowledge exchange among researchers, academicians, and industry professionals. It is heartening to see participants from diverse fields presenting their work on nanomaterials, biosensors, environmental sustainability, and energy storage. Such an interdisciplinary dialogue is essential for addressing the complexities of real-world challenges. I encourage all the participants, especially young researchers, to take full advantage of this opportunity. Interact with the eminent speakers, present your ideas confidentially, and embrace constructive feedback. These interactions will help shape your perspectives and guide you toward impactful research. As we move further into 21st century, sustainability has become a central theme across all scientific disciplines. Material science, with its focus on innovation and problem solving, is uniquely positioned to address this challenge. Developing eco-friendly materials, improving energy efficiency, and mitigating the environmental impact of industrial process are critical areas where the material science can make a difference. Conferences like ICAM 2025 serve as a catalyst for exploring these dimensions and fostering collaborations that drive sustainable solutions. Artificial intelligence is revolutionizing the way we discover, design, and optimize new materials. And the interaction of AI, particularly machine learning and deep learning techniques, enable researchers to analyze massive data sets, predict material properties, and accelerate the development of novel materials with unprecedented precision. AI-driven materials discovery. Traditional material discovery process involve extensive experimentation, which can take years. AI-powered algorithms such as generative models and reinforcement learning can screen millions of potential compounds, identifying promising candidates in a fraction of time. So companies and research institutions worldwide are leveraging AI to discover superconductors, high-strength alloys, and sustainable materials. Predictive modeling and simulation. In this aspect, AI-driven simulations reduce reliance on costly and time-consuming physical experiments. By training machine learning models on experimental and theoretical data, researchers can predict the properties of materials under various conditions, thus enabling the rapid prototyping and design optimization. AI in smart manufacturing, specifically, the role of AI extends beyond the materials discovery into manufacturing. Advanced data analytics and AI-assisted robotics improve precision, reduce waste, and enhance scalability in industrial applications. From nanomaterials to biomaterials, AI is enabling smarter, more efficient production techniques. Sustainability and green materials. In this aspect, AI is also playing a crucial role in sustainability efforts by optimizing the materials composition for minimal environmental impact. Researchers use AI to design eco-friendly materials, reduce reliance on rare elements, and improve recyclability. Despite the tremendous potential, Integrating AI in material science comes with the challenges. Reliable data sets, interpretability of AI models, and bridging the gap between computational predictions and the real world experiments remain key hurdles. However, with the interdisciplinary collaboration and continuous advancement in AI algorithms, we can overcome these challenges and unlock new frontiers in materials innovation. The fusion of AI and material science is ushering an era of accelerated discovery and industrial transformation. As we gather at ICAM 2025, let us embrace this synergy, foster collaborative research, and harness of AI's capabilities to drive scientific breakthrough that will shape the future. Even recently, I am forced to complete 4 courses on AI and successfully to go further on our administration and other aspects. So recently I also completed a course on AI. Let me take this opportunity to congratulate the Department of Physics and dedicated faculties for organizing such a meaningful conference. The department illustrates its history, supported by initiatives like DST FIST, DST SERB, and CSAR funding, is a testament to its commitment to excellence in teaching and research. I also commend the vision of St. Joseph College for integrating scientific inquiry with a societal responsibility. The holistic development of students, coupled with the cutting-edge research, ensures that the graduates of this institution emerge as leaders and change makers. Specifically, the secretary of this college, Reverend Dr. K. Amal, and the principal and other fathers in this college, taking a meaningful and very much effort to bring this college as a number 1 college, not only in the Tamil Nadu or India, but also globally. So we also thank all these fathers for taking their tireless effort to put you in a front areas to work together and give your whatever the support that you request in your college. To the young minds gathered here, I would like to say, let this conference be beginning of the lifelong journey of learning and exploration. Material science is a field that demands curiosity, perseverance, and collaboration. The challenges you tackle today will have a profound impact on society tomorrow. Remember the words of Dr. APJ Abdul Kalam, a proud alumnus of this college: excellence is a continuous process, not an accident. Pursue excellence in your research, seek innovative solutions, and let your work contribute to the greater good for humanity. As I conclude, I would like to reiterate my appreciation for the organizers and participants of ICAM 2025. This conference is a celebration of knowledge, testament to human ingenuity, and beacon of hope for a better future. I am confident that deliberations, presentation, and collaboration that emerge from this event will pave the way for groundbreaking advancement in material science. Let us work together to make this conference a grand success and memorable milestone in the journey of discovery. For the young people, that I want to tell you that today's science is no more valid tomorrow. I can give an example that at the beginning of materials era, we have only metals, then metals, semiconductor, then insulator. Then all of a sudden, we thought that we only these 3. Suddenly the superconductor came into the picture, right? That is a new breakthrough. Even in the superconductor, people thought only metals, only a superconductors. Then alloys came into the field, came into the picture. Then BCS theory was only theory, can predict, because it was possible to predict the TC of the material, and only with the BCS theory you can predict the TC, and people thought that only BCS theory. People have struggled for 70 years and they were not able to break through, and that was broken at 1986. The materials which are not useful, which were thrown out, insulating, antiferromagnetic insulator becoming a superconductor. Why I am telling this? The material which you have thrown out, we thought that it was not useful because we are not tested. Even the human being, we are unable to understand the friends or students or colleagues that how good it is. It takes some time whether really he is a good colleague, really a good friend, really a good student, right? You initially thought that a good student, he was not a good student after a couple of years, right? So that way, that antiferromagnetic insulator becoming a superconductor, then the whole theory was no more valid. The BCS theory was not applicable for this, right? Then it is a copper oxide superconductors. Then people thought, okay, only copper oxide superconductors from 36K to 90K or up to 126. And people thought only the copper oxide is going to rule the world. And that there was many theory was tried, and none of the theory even today, it was not successful. But people at that time, 1987 or 1988, they thought that copper oxide layer is responsible for superconductivity. Then they developed one layer, two layer. The TC was increasing up to 125. Then suddenly that concept was no more valid because the TC was, after increasing a 4 or 5 layer, then the TC was coming down. Then that theory was no more valid. Then copper oxide was responsible for the superconductivity. There are many theories they proposed. But after some time, they tried to dope the iron into the superconductor. Then the superconductivity and the ferromagnetism does not coexist, and it is an enemy. If you dope the iron into the superconductor, TC is slowly coming down and it kills. Then they thought it doesn't coexist, it is always against. There are many papers, many theories are published. Then suddenly, the Japanese scientist, he predicted the iron becomes superconductor under pressure. Iron becomes superconductor. So then again people, why not iron-based superconductors? Why not iron-based superconductors? Then people have found iron-based superconductors. Iron arsenic layer as a superconductor. Now the theory copper oxide is now no more valid. Iron arsenic, iron is against the, people thought the ferromagnetism superconductivity does not coexist. After predicting the iron-based superconductors, the ferromagnetism and superconductivity coexist. That theory, whatever they, hundred thousands of papers are published theoretically, but now the ferromagnetism superconductivity coexists in the iron-based superconductors. So that way, the theory which is valid today and tomorrow it isn't valid. You take a simple example of carbon. Or the allotropes of carbon, initially we thought only graphite, diamond. Then there is a carbon 60 has come. All becomes non-superconductor. And people thought, okay, we cannot predict a superconductivity in the carbon. But all become superconductor. After a certain stage, the iron, how the graphite, intercalating the graphite, it becomes superconductor. And the diamond, you apply a pressure, it becomes superconductor. Intercalating into the carbon 60, it becomes superconductor. So it becomes, whatever you think today, it is, no, you have to think, that's why people always think in a different angle. Mati Yosin சொல்றது காரணமே, we cannot come to the conclusion that this is what. Tomorrow it changes. So the application of the carbon nanomaterials, it becomes richest technology. It gives a lot of advancement in the technology. Once the carbon-based materials, carbon-based nanomaterials, it gives the implication in the industries in an unexpected way. It has given a breakthrough in the industrial sector for various applications. So that is the reason that the theory valid today, people always take, you can take it granted, but also you should think that this can also be broken anytime. So this is advancement in the, even in the after invention of this carbon, all allotropes of carbon become superconductor, there is a single walled carbon, that is also a superconductor. So that gives pave the way for tremendous industrial revolution, which was not accepted before inventing these carbon-based nanomaterials. So people have thrown out the materials are waste, but becomes once again after certain decades, it was giving the industrial revolution breakthrough in technology. So I appeal the students and youngsters, you have to think in an innovative way to give a breakthrough. One student like Abdul Kalam or G.N. Ramachandran, right? So you can enlighten this college and becoming more and more famous, and one idea change your life, one idea change your family, one idea can change the world. One idea can change the world. So you have to think whether you are from do not have the complexity of whether you are from the village or very poor, nothing to do with that. Having idea will shape your future and change your future in a better way. So, and also your life can be changed by interacting with the scientists, friends, and make as much as collaboration. We are able to get 30 projects or 250, more than 250 publication and so many achievements and getting about 12 crore of projects. It was possible only because of numerous collaborations. Except one or students, most of my students visited abroad. At least once, some students 4 times, 5 times, even before completing their PhD. That was possible only because of collaboration. So hence, I suggest the department faculty members and students to enrich your knowledge in a better way. I mean, in a short span of time, you need to have very good collaboration, discussion with your friends and faculties, and it helps a lot to shape their future. At the outset, I thank the organizers, the Department of Physics, and the principal of this college, secretary of this college, and all the administrative personals in this college to giving me this wonderful opportunity to share my knowledge in this wonderful platform. Thank you once again.
Thank you, sir, for your inspiring words. Your insights will surely ignite new ideas. As we come to close this inaugural ceremony, it is my honor to invite Dr. Maggie Diana, the organizing secretary, to deliver the vote of thanks and express our gratitude on behalf of the entire organizing team.
Good morning to everyone present here. It is my privilege to propose the vote of thanks for today's inaugural function of International Conference on Advanced Materials 2025. First and foremost, I extend my heartfelt gratitude to Professor Arumugham, Vice Chancellor of Tamil Nadu Open University, for gracing this occasion as our chief guest and sharing his valuable insights. Thank you very much, sir. I sincerely thank Reverend Father Rector, Reverend Father Secretary, and Reverend Father Principal for their constant support, encouragement, and inspiring words during the felicitation. Thank you, Fathers. As a special thanks to our head of the department for his warm welcome address and our second PG students for soulful prayer song. And also I like to extend my special words of thanks to Dr. Muthupandiyan Ashok Kumar, Professor Pro Vice Chancellor, International University of Melbourne, Professor Dr. Raja Ram Yadav, former VC Veer Bahadur Singh, University Janpur, Dr. Kirti Soni, Senior Principal Scientist CSR, Dr. K. Ramesh, Principal Research Scientist, Indian Institute of Science, Bengaluru, for their greetings and wishes. I also take this opportunity to express my appreciation to all the faculty members, non-teaching staff members, and research scholars, students for their participation and cooperation, making this function a success. Thank you all for your presence and support. Looking forward to a great academic sharing in the upcoming sessions. Thank you very much.
Thank you, ma'am, for the heartfelt thanks.
Good, well done.
Check.
Jai sir. டிரைவர் தெரியும் நம்ம காடை கொடுத்து பார்த்தேன் நம்ம பையனை யாராவது உதவி பையன் நல்லா பையன் மற்ற பெயின்லாம் ஒன்றும் இல்லை, சாப்பிட்டு சாப்பிட்டு
Students, maintain silence. The first session of our day is about to start. dear students and participants, as we move forward in today's enlightening sessions, we now arrive at a much awaited moment, which is the keynote address, which will be delivered by Professor S. Armugham, Vice Chancellor of Tamil Nadu Open University, on the topic of emerging trends in advanced materials. From now on, it is going to be a continuous session of scientific lectures. I request our students to hold on to their pen and notepads to take notes of the scientific events. In order to do the honor of introducing our distinguished keynote speaker, it is my privilege to invite Dr. I. Johnson, convener and head of the Department of Physics, to chair this session and to welcome the chairperson.
It's a great pleasure to have Dr. S. Arumugham, the Vice Chancellor, to chair this technical session, the first technical session of this international conference. Professor at present is the Vice Chancellor of the Tamil Nadu Open University, Chennai. He was the coordinator in the International Relations Center, chairman in various physics forums. He chaired the School of Physics. He was the director for the Center for High Pressure Research at Bharathidasan University. He was the director for the Center for Distant Education. He was the head of the department, visiting professor to University of Tokyo, Osaka City University, Japan. He was the founder, chairman and secretary for MRSI, Material Research Society of India, Trichy chapter. He was the coordinator for UGC 12th Plan, ENCORE. He was a professor of physics at various institutes like NIT and VIT. So Professor is having a rich experience both in academia and research. He was the fellow in Academy of Sciences, Chennai, APAM Association, Associate Academician, Asia Pacific Academy of Materials, China, NAC peer team visit expert member till today, expert committee member in electrosynchronic Trieste, Italy, from 2021 onwards, a prestigious center, international center. Is a mentor in National Institute of Technical Teachers Training and Research Board. He was the executive council member of Indian Spectrophysics Association, ISPA, 2021 onwards. And he held various positions and also holding various positions in the various professional or scientific bodies. He won many prestigious prizes, awards and fellowships to the tune of nearly 20 awards. The new courses he introduced during his tenure as a Center for Distant Education and Bharathidasan University, nearly 12 new courses he introduced in various disciplines. He was the member and board of studies in various institutions like MK University, Periyar Manimai Institute of Technology, Tanjavur Bishop College, Holy Cross College, National College, Alappa University and so on. He was the academic council member from 29 to till today, Veera Vandayar Memorial Sri Puspam College, to 27 Government Arts College for Women, Pudukkottai, Senate member at Bharathidasan University. He held various administrative positions. Besides this, his efficient PhD guidance. He completed nearly 17 PhDs, co-guided 3 PhDs, and at present guiding 8 PhDs apart from 21 MPhils. And the list goes endless. He completed 25 projects to the tune of 3 crores. He was the co-principal investigator for 2 projects. He filed 1 patent to his credit. He is a reviewer of many international journals like Nature Scientific Reports, Physica B, Journal of Magnetism and Magnetic Materials, Journal of Alloys and Compounds, Journal of Material Science, Journal of Cognitive Physics, Journal of Superconductivity and Novel Magnetism, Journal of Intermetallic Compounds, RSC Advances, Materials Chemistry and Physics, Journal of Intermetallics, Journal of Solid State and Science and Technology. So this source is a numerous volume, and I can go on like this. Professor visited many countries, including Taiwan, Japan, France, Germany, etc. And the list, once again the list is endless. So he conducted many programs in Chennai as a Vice Chancellor of the Tamil Nadu Open University. He published more than 300 research papers in various Scopus and Web of Science indexed journals. And he has authored many books also at the international arena. So we are having an eminent scientist, especially in the material science and high pressure physics, in our midst to chair this session. So welcome, Chancellor. Welcome to you.
Thank you, sir, for the nice introduction. The today topic is, since the conference title is on advanced materials, and this magnetocaloric materials and its application is a key area where the technology or the materials development, the last 2 decades, it was a tremendous progress in all over the world. And we have been working on this material for a long time. In that area, we also got a project from Atomic Energy and DRDO. And we established the center for high pressure research. What happens? It's not changing. These are our group members when foreigner Dr. Geeta Balakrishnan visited our lab. It's not changing. See, the plan is to understand the basic thermodynamics, what is magnetocaloric effect, and development of magnetocaloric materials, and examples in oyster alloys and manganites, and important application, conclusion, acknowledgement. So originally developed 19th is theory of steam engines. The scope of thermodynamics is now almost everything, and you know the basics, and you know what is the heat engine, right? And there are 4 laws in thermodynamics, and the MSc students and BSc students knows very well. The key terms here, what is in the thermodynamics that we need to understand, because it is basically on thermodynamics concept mixed with the magnetism. And because the different types of system, whether it is an open system, closed system, or isolated system, right? So what is 0th law? And 0th law of the particle level, and what is work in thermodynamics, and the first law of thermodynamics, you know very well, and what is the relation between the heat and work, and the 2 related terms, what is enthalpy, entropy, what is heat capacity. For this, you need to understand. And what is the second law of thermodynamics, and what is mean by efficiency, what is the Carnot cycle, and what is thermodynamical T cycle, what is entropy of a system. Because this magnetic refrigeration technology, based on the magnetocaloric effect, the application is magnetic refrigeration technology. That is a refrigerator that we are developing using the magnetic refrigeration technology, which is completely free from the compressor or a gas. It is the solid state refrigeration technique, solid state refrigeration technology. You use only a magnet and the sample, use a magnetic field and a sample and water, a coolant as a water. Only these three we are using, and we apply a magnetic field and remove, and to repeatedly do it, it gets cools. So we need to understand what is the entropy, enthalpy, all the thermodynamical aspects. Once you understand these aspects, then it is not be a problem in understanding the development of magnetocaloric material. So the discovery of magnetocaloric effect was the Warburg, German scientist, in 1881, long back, more than 120 years before it was invented. And the property, this magnetocaloric effect phenomena was invented at very low temperature, like around 4 Kelvin. Even to find out the phenomena of magnetocaloric effect, you need to spend at least 10 lakhs on checking. Because you have to have a liquid helium, liquid nitrogen, and you have to cool down and put a sample, put a paramagnetic, that particular material, and find out the phenomena, the concept at very low temperature. So that was, then the advance came by Debye and Georg. Georg found out in 1926 and 97, based on the how it can be cooled with the adiabatic demagnetization. So the process was demonstrated later by Georg and McDonnell, 1933, to reach the temperature of 0.25 Kelvin. So between 1933 and 1997, number of progress was made. So this is made by these three people. They got a Nobel Prize because of their invention in the magnetic cooling. Magnetic, because you are getting the cooling effect by applying the magnetic field on a material. This was reported in 1926. So then after the discovery, the giant magnetocaloric effect. Giant means huge change in the magnetocaloric effect while applying a magnetic field. We call it as a giant magnetocaloric effect based on the gadolinium silicon germanium alloy, and that was a breakthrough. And for this was founded by the Ames lab for this discovery. And see, you know what is refrigeration? Refrigeration is the process of removing heat from enclosed space. That is a simple concept. The primary purpose of refrigeration is lowering the temperature of an enclosed space. So this is the, how does it work? It involves a high temperature reservoir and low temperature reservoir, and what is the work input, heat absorbed and heat rejected. This is a simple representation how the refrigeration works, and the evolution of refrigeration from the 1000 BC to 2020 by developing the compressor-free refrigerator. What is happening? Whatever the compressor, the AC machine or refrigerator, you use a chlorofluorocarbon. And it is very, very dangerous. These gases, if you leak it to the environment, it is very much dangerous to the environment, very hazardous. And it makes a hole in the ozone layer that affects, but in spite of that, there was no way that we are using that, because we cannot live without refrigeration, right? So that is the world that we are having, and these are the cause and effect of ozone layer depletion when the chlorofluorocarbon leaks out. The picture clearly shows how it affects. So the technology that we use, vapor compressor refrigeration, vapor compression technology. So we use that, and whatever household refrigerator or air conditioner that we are using, this is a cycle that we are making, and this is a vapor absorption refrigeration. This is another technology, and this is the schematic diagram of the representation. What is thermoelectric refrigeration? Based on the Peltier effect, where a temperature difference is created by an electric current across the two dissimilar materials, so that we get portable coolers. So we call electronic cooling. So the compact, no moving parts, environmentally friendly, low efficiency, but limited cooling capacity. And this is the example for the thermoelectric refrigeration. Then cryogenic refrigeration, that is possible extremely achieving the low temperature below minus 150 degrees centigrade using helium or hydrogen, etc. And the cryogenic refrigeration, this is the model. And air cycle refrigeration, this is the model. And cascade refrigeration, use a multiple refrigeration cycle with a different refrigerants to achieve very low temperature. It applicable in the industrial cooling and chemical processing. This is a schematic diagram for cascade refrigeration. The next is absorption refrigeration. Use a solid absorptions like silicon gel or zeolite to capture and release the refrigerants under heat cycles. And this is a picture, schematic diagram for absorption refrigeration. Then acoustic refrigeration, this is a model. Then the next is go for a magnetic refrigeration. Based on the magnetocaloric effect, where the material's temperature changes under a magnetic field. Changes, so we call as a green refrigeration, and you can go at very lowest temperature and economically friendly, and expensive material requires for a strong magnetic fields. And this is the process cycle for magnetic refrigeration. So magnetic refrigeration is a cooling technology based on the magnetocaloric effect. This technique can be used at extremely low temperature below 1 Kelvin. As well as the range is used in a common refrigerator, depends on the design of the system. So magnetic refrigeration has been recognized as being an alternative technology. What we have seen several technologies like thermoelectric and other techniques, but the alternate method which is viable in future, it is possible to give a breakthrough in the world. Only the magnetic refrigeration technology for the replacement of present conventional vapor compression technology. So this is a simple magnetic refrigeration cycle. You take a paramagnetic salt or a paramagnetic material, before applying a magnetic field, the spins are oriented in a random direction. Once you apply a magnetic field, the spins are, you can see that it is parallel to the direction of the applied magnetic field. But what happens once you apply magnetic field and the spins are, because there is a change in entropy now. There is a disorder to order. There is a change in entropy. Then it gets heat up. Now, once it's heat up, you have to remove the heat by using a simple water. So the process is called adiabatic magnetization. Adiabatic, because without changing the spin orientation, just you are removing the heat, you are keeping the magnetic field on application. What happens once the heat is removed? Okay, then you have the isomagnetic enthalpy transfer. So once it is, the temperature is removed, the heat is removed, then you remove the magnetic field. Then again it goes to the random direction. So this cycle repeats a number of times. So application of magnetic field and remove application. Either you keep the sample constant, take the magnetic field, apply and come away, apply and come away, apply and come away, or keep the magnetic field is constant. You take the sample close to the magnetic field and remove it. So either way that is possible. You can attain the low temperature by just applying a magnetic field and remove. If the cycle repeats, then the temperature cools and you can get a very good cooling. So no gas, no compressor, nothing. So it is a viable technology for the existing, for the alternative for the existing conventional vapor compression technology. So this magnetocaloric effect is a magnetothermodynamical phenomena in which reversible change in temperature of a suitable material for cause to exposing the material to change a magnetic field. To change a magnetic field. So in this material, significant change in entropy. It goes to disorder to order, again order to disorder. There is an increase or decrease in entropy causes the cooling the sample at lower temperature. So we call it as a magnetothermodynamical phenomena. So that's why initially we reviewed the thermodynamical concepts that we need to understand. So cooling and heating is in a magnetic material by applying the magnetic field. What is the origin? The origin is a coupling of the magnetic sublattice to the applied magnetic field changes the entropy of the system. In any material, there is a spin orientation in each layer. How the spins are oriented, how these spins are interacting with another sublattice, whether it is connected ferromagnetically, whether it is coupled antiferromagnetically, or how it is coupled from next to next layer. So this entropy change in the system or the effect of magnetocaloric value depends on the magnitude of the magnetic sublattice, how it is coupled. So that is the reason, and you can see here. So the increase in the magnetic field increases the magnetic order and decreases the entropy. Decrease in the magnetic field decreases the magnetic order and increases the entropy. So the large magnetic field, if you apply, you will get a large magnetocaloric effect. So one needs a ferromagnetic material with a Tc around room temperature, because the first it was invented at very low temperature, and this is the thermodynamical steps which already that we have described. Step 1, step 2, step 3, step 4 for a complete cycle. The cycle can be repeated in a number of times, and whatever the temperature that you want, you can achieve at very low temperature, and the time depends on the amount of cooling, how fast it goes, depends on the magnetic field, depends on the material. You have any magnetic material, you have the any kind of ferromagnetic material, you have the susceptibility. Okay. The next is what is all the 4 cycles. Is the first cycle is adiabatic magnetization. The next one, this is the how the spins are orienting the picture. Because I have given only 30 minutes time, that's why I am moving it fast. Okay, then isomagnetic enthalpy transfer, the second step, and the third, this is the how it happens. The third step is the adiabatic demagnetization, and where the substance is returned to another adiabatic in the condition, the entropy remains constant, the magnetic field is decreased to 0. So thermal entropy causes magnetic moments to overcome the field and sample gets cool. So this is the how it happens. So the last isomagnetic entropic transfer, and this is the view, and see this is the view, just keeping the magnet is constant and you are moving the sample up and down. So you just close to the magnetic field, apply and remove it. So the magnetocaloric effect that can be clearly understood by this. And this is the overall, this is the conventional one, the piston cylinder with the vapor compression technology. How the Carnot cycle works for the vapor compression technology, and here how the structural transition or the volume change, etc., how it connected from thermodynamically in the first order. So this is the working of the magnetic refrigerator. This is a flow chart, and you can understand how they have decided. So how you can calculate the magnetocaloric effect? So initially one has to find out the temperature dependence of the magnetization, then find out where is the Curie temperature and whether is the hysteresis there or not, whether it is the material is the first order or second order. Then you have to go for the field dependence of magnetization nearer to the critical temperature. For example, the critical temperature, the Curie temperature is say 100 Kelvin, about 20 Kelvin, below 20 Kelvin, with the interval of few Kelvin, 2 or 3 Kelvin, do the field dependence of magnetization. Then you can measure using the formula delta Sm. Then you can find out the magnetocaloric effect, and also you can find out the relative cooling power. Generally, for investigation of magnetocaloric effect, one is the direct method, another one is the indirect method. Generally, people are using indirect methods. Characterization of magnetocaloric effect by a direct method, but this is the most straightforward method, but it's very difficult to do for all the sample at temperature, but people can do it, and this is the how you are using it. And generally people use indirect method by, as I said earlier, by if you have a good vibrating coil magnetometer or vibrating sample magnetometer or squid magnetometer, you can measure the temperature dependence of magnetization and measure the field dependence of magnetization, and you can measure it. So the magnetocaloric effect depends on the strength of magnetic field and temperature and H. So the error is about 3 to 10%. This method is very useful for a rapid search of potential magnetic refrigeration material. For large, good MCE material, you large dou M by TH by dou T. So we need a ferromagnetic material with a TC around room temperature, and there is a two effect is there. One is normal magnetocaloric effect, another one is inverse magnetocaloric effect. So from the equation that you can understand, the MC is proportional to derivative of magnetization, magnetic field variation. So the large value of derivative of M, you will have large MC. So you will get dou M by dou TH less than 0. The delta Sm is negative for a positive magnetic field change. Delta H, this is called as a direct magnetocaloric effect. If the positive isothermal entropy change associated to the positive magnetic field change, it's called inverse magnetic caloric effect. This is an example. You can see that the temperature dependence of magnetization, and you can see that there is a hysteresis, and you can find out the Curie temperature. And now you have to do the field dependence of magnetization every 2 Kelvin interval, and from this you can find out the magnetocaloric effect, and you can see the delta Sm versus temperature, and you can see how that you can find out. Similarly, you can also apply a pressure and how the magnetocaloric effect changes. What is the importance of doing pressure? Why it is needed? Because once you apply a pressure, whether it is increasing or decreasing, once it is, you get a drastic change, a very good change by applying a small pressure. What you can do is you can, by doing the replacement of certain atoms and do the chemical pressure on your sample, the same effect that you can get without pressure. By generating a chemical pressure at atmospheric pressure and by replacement of proper size of atom, create a chemical pressure so that you can get the same change that you observe under pressure, that you can get ambient pressure. That is the use of, it's only basic research, but tells for developing new materials, increasing the efficiency of the material. Otherwise, randomly you cannot dope a material. Once you want to do systematically, you need to do systematic studies under pressure. So over the past 70 years, there has been an upsurge in the knowledge of magnetocaloric effect. Many materials have been investigated. Number of new materials have been discovered, and the best material is a gadolinium in a periodic table. but very highly expensive gadolinium and gadolinium based alloys are the best magnetocaloric material, and you can go to very low temperature. So recently the rich physics and prospectors were people have found, and the best material are oyster alloys and manganites. So this magnetocaloric and order of phase transition. So MCE and its dependence on temperature and magnetic field and the nature of magnetic phase transition. If it is a first order field induced paramagnetic to ferromagnetic transition, is a magnetic disorder to order. Magnetic disorder to order, and it gives a high magnetocaloric effect. This originates from the difference in magnetic ordering between the two magnetic adjacent phases or sublattice. The magnetic spin system coupled with the external magnetic field is a consequence of large magnetocaloric. When you apply a magnetic field, how the spin orientation in a sublattice respond to the magnetic field. Very simple, right? How the spin orientation respond to the applied magnetic field, and also how it contributes the next layers for the application of magnetic field. You need to understand theoretically and experimentally comparing the data, and you need to understand the origin of magnetocaloric effect. It varies from one material to other material because spin orientation in one lattice to the other lattice, one layer to the other lattice on a different materials are not same. It is different. So for each material, one has to understand what is the origin of magnetocaloric effect. It is nothing but the application of magnetic field. How it responds, the spin orientation responds to the applied to the magnetic field, how it affects, how it changes by applying and removing it. So material with the first order shows a large magnetic entropy change, small hysteresis accompanied with the structural transition but mechanically unstable. These materials are mechanically unstable, but materials with a second order transition shows a smaller magnetocaloric effect, broader in the hysteresis and with a stable structure. With a stable structure. And this is the way how you can calculate the relative cooling power. And this is the hysteresis, how it connected to the magnetic field. So you know what is hysteresis? No need to explain. And this is the magnetic cooling cycle of single MCE material for one cycle that you can see about the hysteresis and what is the delta T and what is the delta S, etc. And this is the different materials of first order and as well as second order transition, whatever reported with a magnetic field of 2 Tesla. And this is how the gadolinium based alloys, oyster alloys and manganites, what are the atoms are mixing with these alloys. Mixing with these alloys. And what are the impact? Any material cannot be magnetocaloric effect. It cannot give. And what are the expected characteristics of good magnetocaloric material? Okay, so the MC is an intrinsic property of a solid. Years of application and removal of magnetic effect is desired. It is the individual characteristics, strongly depends on Curie temperature, degree of freedom for a magnetic dipoles during ordering and randomization of materials. The originally suggested refrigerant was a paramagnetic salt, such as cerium, magnesium nitrate, gadolinium and its alloys are the best materials. And the criteria for selecting a good magnetocaloric material, it should have a large magnetic entropy change, large adiabatic temperature change, small lattice entropy, high divide temperature, nearly zero magnetic hysteresis, very small thermal hysteresis, small specific heat. These are all the important characteristics of any magnetocaloric material for making use for the magnetic refrigeration technology. And these are the examples of different, with a different period and with a different capacity, what are the materials were reported. And these are isoalloys and manganites. These are again on manganites. And what are the materials that we studied at the Center for High Pressure Research, Bharathasan University. And these are all because it was invented 1884, very low temperature at 4K. But in the last 15 years, there are more than 500 materials invented, and the Curie temperature was invented instead of 4K at room temperature, even above room temperature. Now you don't need to spend huge money for investigation of magnetocaloric effect on the new materials, because at room temperature and above room temperature, that is the way. And these are all the examples, new materials, and how the giant magnetocaloric effect on these materials. Isoalloys, some of our results, simply that you can say that temperature dependence of magnetization, and you can zero feel cool and feel cool, and you can see that you could find out where is the hysteresis, where is the Curie temperature, and other magnetic transitions that first you have to study from room temperature to 1.8 Kelvin. Then you have to choose that particular Curie temperature, and below and above study the field dependence of magnetization. You can see that this is the field dependence of magnetization, the smaller intervals below and above the Curie temperature, and then you calculate the magnetocaloric effect and at different temperature. And this is the plot when you chose near the Curie temperature the highest value. Near Curie temperature, the peak shows highest. When you increase the magnetic field, it also increases. So the magnetic caloric effect can be increased by increasing the magnetic field. This is an NIM and vanadium gallium alloys, and for different compositions. And this is a relative cooling power, and this is again on nickel manganese tin alloys, and again the magnetocaloric effect calculations, and this again NIM and ESM, and you can see that this is again the magnetocaloric effect value, and this is our again results on prosodium calcium manganese alloys. And this is the cost, how it is going year by year. Once you find out the materials, this is the known magnetocaloric material between 100 to 300 Kelvin starting from GD2 on various materials, and you can see that less than 100 Kelvin. So this is a comparison, how the value of delta ISM is higher on a selected materials now presently used for the developing the magnetic refrigerator. And this is a reported MCE materials, and this again you can choose on different materials which is the best. From this diagram you can choose. And you can see here how till 2000 there was not much drastic, and the number of papers published are very high after 2000. After 2000, but it was invented in 1881, right? But only in the last 20 years, the progress was very fast, and new materials have been invented, number of papers were published, and the development of the products are expected in 2030 or something like that, and still people are trying to find out these you just see that comparison between magnetocaloric, electrocaloric, multicaloric, etc. But so which is the best is a magnetocaloric is highest comparison with this is the viable technology. Why? Because if you go to DMRL Hyderabad, and you know that in our MSc lab, the 2 Tesla magnet, even 10 people cannot carry. Such a huge, right? It is 1 Tesla or 2 Tesla. But now the present technology, I can put 10 magnets or 20 magnets in my pocket with a diameter of say, நம்ம 2 ரூபா காயின் இருக்கு இல்லையா அந்த சைஸில் you have 2 Tesla, 1 Tesla. Which shape you want? Rounda வேணுமா, you want any shape? And DMRL, for example, makes, and other parts of the world also, they are making the technology, how the permanent magnets change the size and shape and the cost from 20 kg to a few grams. Now, why I am telling this, still for why the material is, this technology is not coming to the market, we need to develop the standard magnets with high field, with a smaller in size. And we need to find out a high efficient magnetocaloric material so that the cost will be cheaper. Otherwise, gadolinium and all 1 gram is about 40,000, 50,000. So it is not affordable. Overall, you develop the magnetic refrigeration. People have developed the magnetic refrigeration technology, and they developed the refrigerator. The refrigerator that we use for 20,000, the same refrigerator you want to use it in this technology, you need to spend 2 lakhs. So commercially now, it is not viable. That is the reason it has not come into the market. Okay, it is still anytime the breakthrough comes, and this will come to the market. And this is the room temperature magnetic refrigerator materials. I am showing their examples. And these are the companies like involved, Samsung Electronics, Whirlpool, Toshiba, General Electrics, etc. They still today they are struggling and fighting and trying to find out new materials and improving the technology on this magnetic refrigeration technology, invested billions of dollars, and they are in the process. And if someone break through on new materials with high efficiency, the next day it will come into the market, even it will come to the free scheme. Because you can hang it anywhere, you don't need these number of AC machines, because the efficiency is double the efficiency of what we have it now. And you can hang it in the wall. You can, once the seminar is over, you can take it to another room and you can hang it like a wall clock. That is an advantage once it is come into the commercial market. So these are the companies involved. And this is an example, GD-based refrigerator developed in 1997 with efficiency of 60%. And this is a GE company developed. And it is potential application, as you know, the world technology will get changed because it applicable in air conditioning, small scale water cooling, small refrigerator, food preservation, and even the for farmers, and dehumidification, beverage dispensing, and even the transport cooling, right? And central cooling system in a mall or a hut, anything in the medicine. So this technology goes deep into all the sectors of the present, the requirements, whatever we have it, the world will change once the TV has now come into the different shape and size, right? Now come into our hands, right? That way it will change the world if it comes into the market. It's not changing. So what are the advantages in this? Because you can do the cooling in electronics, personal cooling, commercial, industrial purpose, food preservation, medical, etc. What are the advantages compared to the present technology? It's a green technology. No use of conventional refrigerants like chlorofluorocarbon. No environmental damage. No harmless to the environment, and no noise. Compressor, no more compressor, no noise. தொல்லை விட்டதுப்பா அப்படின்ற மாதிரி தான். Because the maintenance will be less. Once you don't have compressor, the problem is less. Noiseless technology, high efficiency, about 70%. You have the 60 to 70% efficiency. Then it becomes simple in design and low maintenance costs. No toxic. No toxic. And no use of conventional refrigeration, what we are using. And also the efficiency about 70% compared to the present 35% or 40% maximum that we get. And maintenance costs, because of that you will get less costs and less expensive. Once it comes into the, now it is more expensive, but once it comes into the market, it is less expensive. So energy, so in this whatever the summer or any other time, what is the electrical amount of electricity that you use, 50% or more than 50% can be reduced. So that means the whole world, the utilization of electricity comes down to 50%. That itself is a great saving. And reduce hydrocarbon emission. No gaseous refrigerants. Overall, this technology is very good, but we have a little disadvantage at the present state, and it has a lot of, including space technology, it has a lot of potential application. Only thing is, we need to find out what are the obstacles that we have to remove it, and we have to bring it to the reality for a day-to-day human utilization, day-to-day activities. For that, any of you can break, or any other person in the world can break, the technology will come into the market. So this is the way that we have to, young people can think and entering into this field, understand the field and develop, use your innovative ideas, and Nobel Prize is yours. Nobel Prize yours. Because in the superconductivity in 1986, people got their Nobel Prize within 3 months. Because it was a breakthrough. And your Nobel Prize also breakthrough. None of them has got a Nobel Prize in a 3 months of time till now. But 1986, the student and teacher has got the Nobel Prize in 3 months of time. Because of the commercial importance, breakthrough for, 70 years of the study has broken and the record, then it was given. And for this, if suppose you make a patent on this, you are the number one richest person in the world. If you develop a good technology with a good material, if you make a patent it, you are the king of the world. No doubt on it. Anybody can become. Only thing is, you have to innovatively think and make a breakthrough on it. Okay? So, you have to, whatever the challenges that you have to make it, the conclusion is the magnetic refrigeration technology has been recognized as worldwide alternative technology to the present technology, could be in room temperature, that can be easily used, the magnetic refrigeration technology. It can replace the current technology. The discovery of outstanding MCE materials provided new opportunities, new avenues in the world. It is alternative working material in the magnetic technology. It is believed that the magnetic materials with the superior magnetocaloric properties, in addition to cheap materials processing cost, will be the option for future magnetic refrigeration technology. So it is a revolutionary technology, green alternative. You get the scientific advancement by finding out the new materials. It goes a lot of application. It's a promising for domestic and industrial cooling. And cryogenics you can get enables an ultra low temperature system for scientific research. The challenges are high cost of the rare earth materials need for a strong magnetic materials and material optimization. That you have to find out the cheapest material and get the magnetocaloric effect with a low magnetic field. How it becomes cheaper, the material cost should be cheaper and the magnetocaloric effect should be, the efficiency should be very higher, the material cost should be cheaper and with the response to the low magnetic field. The magnetocaloric effect, you should get high efficiency with a low magnetic field. So it has a good prospectus and it has a good sustainability in this world and good impact in the technology of the future development and future's humans' life. So I thank all the funding agencies supported for our studies and also I thank the organizer and the team, especially Professor Johnson, for giving me this opportunity and the management. Thank you one and all.
Thank you, respected Chancellor. So, if you are having any questions, you can contact our Professor and Chancellor directly. For the time being, we are having 2 more sessions before lunch. So, I will wind up with this. I sincerely thank once again for our respected Chancellor for coming all over from Chennai to Trichy and to give a useful insight for our collaboration. Vice Chancellor. Okay. Thank you.
I would like to take a moment to extend our heartfelt gratitude to our respected chairperson, Dr. I. Johnson, and also a special note of appreciation to our esteemed keynote speaker, Professor S. Arumugam. Thank you, sir.
We have an exciting talk on superconducting and normal state properties on high entropy alloy superconductors. We welcome Professor A. Patrick Prabhu and Dr. Manikandan Krishnan on the stage for the second session. Now, I invite the chairperson, Professor A. Patrick Prabhu, a noble teacher and esteemed academician who has been instrumental in making future scientists in our department. I now request the chairperson to honor our speaker, Dr. Manikandan Krishnan, with a memento. Thank you, sir. Now, I kindly invite Professor A. Patrick Prabhu, Associate Professor of Physics, to chair this session and introduce the remarkable achievements of our speaker.
A very good afternoon to one and all gathered here and technically connected here. High entropy alloys, in short HEA, are a recently opened research area in material science and condensed matter physics. Although 3D metal-based HEAs have already been the subject of many investigations, studies of HEA superconductors, which tend to be based on 4D metals, are relatively fewer. Due to their unique properties like high current density and ability to operate under curious conditions, they have potential applications in the area like very high magnetic field, superconducting And today, to explore more into HEAs, we have Dr. Manikandan Krishnan in our midst. Dr. Manikandan Krishnan is working as a research scientist at Shandong University of Technology, China. And on the behalf of our department and college, I extend my warm welcome to you, sir. Dr. Manigandan did his BSc Physics at Bishayibar College, Trichy, MSc from Bharidasan University, Trichy, MPhil Physics from Pondicherry University, and obtained his PhD degree from Bharidasan University. Research experience. Sir joined Bharidasan University as a research assistant in the year 2012, and after his doctorate, he joined as a research scientist at Laboratory of Functional Molecules and Materials, Shandong University of Technology, Shandong, China. Sir is an expert in handling single crystal growth using CVT, arc furnace that is used to fabricate polycrystalline samples, PPMS, that is physical property measuring systems, and MPMS, magnetic property measuring systems, etc. Sir's area of interest are a study of heavy fermions, 2D layer high entropy superconductors, low dimensional quantum materials, low temperature and high pressure instrumentation, study of hexaferrites and TCO materials. Awards. Young Scientist Award in the year 2019, Project Assistant in the year 2012, Junior Research Fellow in the year 2015, Junior Research Fellow again in the year 2016, Senior Research Fellow in the year 2018, Visiting Researcher, ISSP, University of Tokyo, Japan in the year 2019, and Visiting Researcher in the year 2023, and again at USSP, ISSP, University of Tokyo, Japan. Sir has published more than 30 research articles in the well-renowned international journals and has authored a book. And Sir holds a H index staff number 10 and I-10 index number 12. Such an eminent person is in our midst to deal with eminent materials. Sir, now it is over to you. Thank you.
Thank you, sir. Here I am going to discuss about the superconducting and normal state properties on high entropy alloy superconductors. I am working as already professor discussed about my profession. So here I am going to discuss about the high entropy alloy. Why high entropy alloy is immense in these properties? Because high entropy alloy is one of the very good functional materials in the various type of applications. But the high entropy alloy discovered in 2003 only. When it was discovered, it's only formed the corrosion compound. So they want to reduce the corrosion. So it is an alternative of another metal alloys like steel alloys. So when it forms the high entropy alloy, it's only based on the alternative of metals only. So after discovery of high entropy alloys, it survives everywhere. When it goes for the energy material applications, nowadays it is used in hydrogen storage material and superconductors and magnetic refrigeration materials, and everywhere it is a very goes on. Everywhere it goes on. High entropy alloys consist of 5 or more elements with the high entropy alloy is composed of 5 or more elements with the composition of 5% to 35% of composition are close to the ecoatomic ratio. HEA structure is characterized by a topological order lattice combined with an exceptionally high degree of chemical disorder, often linked to the metallic glass on an order lattice. In HEA were first discovered in 2004. Generally, the HEA is based on 3 simple crystal lattice: BCC, FCC, and HCP and CSCl. When it is discovered, first it goes on FCC structure only, because when they formed with the 3D elements, 3D combined elements, automatically you can find only the FCC structure. Later on, BCC and cesium chloride structure has been developed. When it forms high entropy alloy, it should satisfy 4 different effects. The core effect belongs to high entropy effect, lattice distortion, sludges diffusion, and cocktail effect. The high entropy effect is nothing but the stabilize the structure formation. When it goes for the combination of 5 different elements with different atomic size, it should exhibit standard crystal structure. So high entropy, it should exhibit the high entropy effect. And lattice distortion means the different type of atomic size will combine into single crystal lattice. So automatically the stress will be occupied in the lattice strain. That lattice strain will form the lattice distortion on the crystal. So sludges diffusion, the sludges diffusion is due to atomic diffusion. It leads to the lattice potential order, it's induced the atomic diffusion. And cocktail effect is nothing but a multi-component effect. When you form the compound, it's 2 or 3 metals in the overall property combined with all 3. But here is a 5 or more elements. When you form the 4 or 5, combine 4 more elements, the property should be in overall from the elements. The formation of high entropy alloys. Initially, the high entropy alloy starts from only the combination of 3D elements with the combination of light elements like lithium, beryllium, magnesium, scandium, and aluminum only. Later on, when they discovered combined with 4D and 5D elements, the behavior is completely different. Because when the combined with 3D elements, it exhibit BCC, FCC, and SCP structure, it's our non-superconductors. So they exhibit either maybe the ferromagnetic or paramagnetic salt. When combined with 4D and 5D elements with the mixing of 3D element, it exhibits some different behavior with a diamagnetic signature. At that time, there is no observation in the superconductivity, so it's a diamagnetic nature. Once they formed the single phase compound, so it exhibits the superconducting nature. Because why the superconductor is very important for single phase means, if you combine the combo different elements, it exhibits 2 different phases. If it exhibits some other property means, if magnetic property means, you can differentiate either in magnetic cooling and warming or some magnetic isothermal curve. But in the superconductor, if it exhibits superconductivity in multi-phase component means, which is arise due to the superconductivity, that we can't know. So first of all, we should focus on single formation phases in the high entropy alloys. So based on the properties, the high entropy alloy applies everywhere. Shape memory alloys, magnetocaloric effect, superconducting material, catalyst material, thermoelectric materials, energy materials, and radiation production and environmental application. Nowadays, the gas storage, it's very difficult. Nowadays, the observation is very close to sulfide compound. So it's 2D only. It's not a bulk compound, it's 2D compound. So nowadays, high entropy alloys, we can't succeed as a single material. We can apply this type of material in every application like that. So formation of high entropy alloy. Why we need a superconductor in the multi-component system? Nowadays, the application point of view, the superconductor is efficient only in NBTI material only. Because it should have high critical field, it should have a high critical temperature, then only you can go for the commercial applications. But when you go for the binary superconductors, it exhibits very high ductile value. But the replacement of NBTI, now itself there is no combination of replacement of NBTI superconducting magnets. So afterward there is a replacement of A15 compounds, but A15 compound there is some significant drawbacks on the structures. So after that there is one of the very good replacement for the superconductor is multi-component system with a single phase. So this is the first superconductor in 2014 at 7.3 Kelvin with BCC structure. The formation of high entropy alloy based on from the element or from the binary superconductor or from any of superconducting compounds. But it should not change the structure or if it is change the structure means it should be in a single phase compound. Because in 3D elements, many of the superconductor at ambient pressure. Example, Nb is a very highest Tc, superconducting Tc in the 3D elements. It is a temperature is 9.2 Kelvin, but some of other elements are very less compared to other niobium. So when they form the superconducting behavior in this compound, it may belongs to Nb, but the structure is different, completely different. So afterwards, the BCC, it share each side share with 5 elements. So BCC is a crystal structure. When we go for the A15 compound, it may orient randomly with the crystal sites. So we couldn't find where it orients with the A15 compounds. So that is a main drawback for A15 compound from for the high entropy alloys. So from when we form with the niobium free compound, so we focused on either maybe 3D, 4D mixing with 5D elements, or except with niobium, we can mix with 4D, 5D elements to form the superconducting compound with a single phase. So why valence electron? VEC means it's a valence electron. The valence electron count is very important for the superconducting high entropy alloy, because when you mix with more than 5 different elements with atomic size means automatically the high entropy effect will be high compared to sludges effect. But some of the compounds, the sludges effect is high means automatically the phase will be either it may be in more dominant phases will be high, or its coexistence with 2 different phases. So when we focus on the structural basis, so we should focus on valence electron count. First we should, once you form the high entropy alloy, first you should fix the VEC. If it is example at 4.6, so accordingly I can choose either 3D, 4D or 5D elements to form it's close to 4.6. So in the type A, type C, type B means the type A belongs to BCC structure, and type C belongs to cesium chloride structure, and type B belongs to non-centrosymmetric, that is alpha Mn structure. The maximum Tc observed in 4.7 Kelvin in BCC structure, at 5.9 there is a maximum Tc observed in cesium chloride structure at ambient pressure. This is the maximum Tc observed nowadays in these compounds. So superconductivity everyone knows about. In superconductor means it should exhibit 3 mechanisms. One is Meissner effect and zero resistance and flux quantization. Once the material exhibit these 3 properties, then only you can call it as a superconductor. Some of my work has been presented. The superconducting ground state and electronic properties of sigma phase Ta, tungsten, molybdenum, rhenium, osmium, high entropy alloys. Why we form with niobium free compound means our ultimate aim to form the niobium free high entropy alloy with another structures, not BCC structure, because we focused on binary alloys. We are not starting with elemental superconductor. We start with MORE, that is a binary superconductor. MORE is a very good binary superconductor. So we start with MORE with addition of some other element to form the single phase in this compound. So the synthesis of arc melt, high purity of arc melt furnace, the XR. From the XRD, the labile fit conforms the sigma phase of all 3 compounds. So it's completely different from the niobium based compounds. Because in sigma phase, when you want to form a sigma phase in the high entropy alloy, you should you should know about the sigma phase where it is formed. You should have either the parent compound should exhibit sigma phase or not, or any other secondary phase. So MORE is a very good compound for the sigma phase. When you add with any other material, so the sigma phase stabilized until actually we increasing the tantalum concentration. We fixed with osmium and tantalum. So just now we change with tungsten only. So from this, we observed only pure sigma phase observed in this compound. The all 5 crystalline lattice, the randomly oriented with all 5 elements. So we couldn't observe any secondary phase or secondary elements in our samples. So from the resistivity analysis, so we observed the 6.14 Kelvin at parent compound. When increasing the pressure, when increasing the doping concentration, so the superconducting TC automatically decreased. So W is one of the finest element in the sigma phase compound because MORE, it exhibits sigma phase. At the same time, WOS and WRE exhibit also sigma phase. So when increasing the sigma, when increasing the tungsten concentration, TC may be decreased. At the same time, the resistivity is completely independent of temperature at above TC point. So this we need to analyze because when you decrease the temperature, the resistance should be decreased as per our law, thermodynamic law. But Ohm's law, sorry. When we decreasing the temperature, the resistance are almost independent. So that we need to find which type of scattering belongs to the normal state of this compound. So that's why we used Bloch-Greenson function and Fermi liquid model to find the electron-electron correlation or electron-photon correlation, which is dominant in this compound. So we find electron-electron scattering is very weak in this compound using this formula, using these models. And the temperature-dependent magnetization shows the bulk superconductivity. The bulk superconductivity find means when it is the difference between the zero field cooled curve and field cooled curve, it shows the bulk superconducting nature, and also the shield diffraction is more than 100%. In isothermal curve also, it shows some hysteresis loop in the isothermal curve. So it is also one of the confirmation for the bulk superconductivity. When increasing the W concentration, the bulk superconductivity remains constant. So in superconductor, the critical field analysis is very important. When you find a superconductivity, it should exhibit, it should have a high critical field where the superconductivity vanishes. That is a critical field analysis. From the isothermal magnetization, we can find the lower critical field. It is a single vortex region. When it goes for the temperature dependent resistivity with various applied magnetic field, so we can find from the upper critical field from these resistivity measurements. From the thermally activation flux flow model, thermally activation flux flow model is one of the very efficient method to find the vortex movement of the sample at the superconducting state. When you take a resistivity, temperature dependent resistivity at various magnetic field, you should use the Arrhenius plot. You should use the Arrhenius plot to find the activation energy. So belongs to the activation energy with the magnetic field. So we may distinguish between the two states. So the double linearity curve confirms the vortex motion will be the two different phases. One is the single vortex region and another one is the collective pinning state. The single vortex region is completely superconducting state. When the collective vortex region, there is a vortex movement observed in this compound. The flux pinning behavior is due to only either it may be the point or planar. Why it is important means the flux pinning behavior arises due to the either defect or something it's happened. Because in high entropy alloy, the disorder is highly disorder observed in this compound. That's why the collective pinning vortex state is very important for this compound. When increasing the tungsten concentration, the vortex movement the single vortex region will be decreased, and at the same time collective vortex region will be increased. It's due to the planar to point effects of the pinning sites is indicated by the significant increase in alpha values, both lower and higher upright field. Because when you fitted with the power law behavior, the double linearity observed in this compound, when you found the double linearity in the Arrhenius equation, So you should know, you may understand there is a vortex movement observed in this compound. So specific heat analysis. The specific heat analysis we can in two ways. One is the normal state and another one is the superconducting state. So when you go for the superconductivity, the specific heat is one of the very good confirmation with the confirmation of these samples. Because when you take a temperature dependent specific heat, there is a sudden jump in observed in particular temperature that is called a superconducting transition temperature for this sample. When you use the Debye temperature, Debye model, we can find some Debye temperature and Sommerfeld coefficient for Sommerfeld coefficient at normal state. We can find which type of behavior observed in the normal state. When go for the low temperature at superconducting state, we fitted with BCS model. Why we fitted with the BCS model means how to calculate the superconducting gap in this compound. So we are using BCS model to found the superconducting gap at superconducting state. So we fitted with BCS S-wave fit. It explains the superconducting wave, superconducting gap decreased with the W concentration. Here, figure D stands for the superconducting TC depends on Sommerfeld coefficients. So it replicates that the superconducting TC, there is no direct connection in the Sommerfeld coefficient, but it is a direct relation between the density of states in the compound. And also the volume is directly linked to the superconducting TC. And another one is the electron phonon constant is directly linked to the superconducting compound, superconducting TC. So once you found the compound, you should categorize the compound. Either it may be the conventional or unconventional. When you go for the superconductor, the two types of superconductor based on the properties. One is the unconventional and another one is conventional. The conventional means it belongs to binary superconductor. And in unconventional means the property is completely different from the conventional superconductor. So as per VEC formula, valence electron count, so it belongs to the high electronegativity side. So the sigma phase compound belongs to the electronegativity side as per alpha M, non-centrosymmetric compound base side. From the Umura plot is confirmed that differentiate the sample between the unconventional and conventional behavior, conventional superconductor. So the sample belongs to the conventional behavior of superconductor. And another one is structural evolution of superconducting properties of MORE, RUPD and TAW, tantalum, tungsten, molybdenum, REOIs, high entropy alloys. So the similar properties we observed in this compound, because in this we observed some phase transition due to the chemical pressure. So when we change the interchange of the elements, it observes some phase transition in this compound corresponding BCC and tetragonal and hexagonal structure we observed. The similar superconducting properties compare between the previous sample. So here we compare the superconducting property with the binary MORE compound. And another one is we found some phase change observed in this compound. When we interchange with this compound, interchange the concentration with this compound, we found the phase transition from BCC, sigma type and alpha Mn type we observed in this compound. So it is also belongs to, finally it is also from the Umura plot, it confirms the conventional nature of the superconductivity, but it is completely different from the previous sigma phase compound. So this is some BCC structure alloys. The pressure effect on high entropy alloys. So we found some BCC alloys. So we measured the temperature dependent resistivity under high pressure up to 50 GPa. So there is an increase in TC up to 50 GPa. So we find there is no structural transition in this compound. And also we found some band structure for this compound. So in band structure also, we found that there is a significant changes in the Fermi state. So now itself we are in progress of this compound. We further increase the beyond the above 50 GPa to why this type of, how the Fermi state observed in this band structure changes in the Fermi state. Because when we increase the pressure, there is a significant changes observed in this Fermi state. So it belongs to the superconducting. It belongs to only the superconducting. It may enhance the superconducting nature of this compound. So that's why we believe that we go beyond the 50 GPa means there is a significant observation in the experimental observations. So conclusion, the new series of high entropy alloy in tantalum based and MO based using arc melt method resulting in a single sigma phase structure. The investigation of the electronic specific heat capacity in the superconducting state of HEA reveals the BCS type weakly coupled fully gapped superconductivity. The Umura plot confirms the conventional superconductivity nature. The BCC alloy unveils the superconducting TC at 5 to 8.1 Kelvin at 50.2 GPa increases with the external applied pressure of 50 GPa. The volume compressed by the application of pressure confirmed from the high pressure XRD measurement without any secondary phase. The mystery of superconducting nature of HEA is robust with the chemical and external pressure. The future study will focus on the various HEAs to clarify the robustness of the superconductivity. So I acknowledge to my group leader, Professor Bolio. So he is my mentor. So he gave wonderful freedom to work in the field of superconductivity. And Professor Iwatoko is working as a professor in Institute of Physics, University of Tokyo. He gave me the wonderful freedom to work in his laboratory for the 3 months to measure the superconducting behavior of compound. So I thank to Professor Arumugham. He is my PhD mentor. So Shandong University of Technology. Shandong University Technology is one of the very big institute in the Shandong province. So it has a very huge department and very reputed infrastructure in that laboratory, in various laboratories. So totally 34,000 bachelor students are currently studying in institute, and 3,700 master students are studying in the Shandong University of Technology. There is a 20 university research institution in Shandong University of Technology. There is every year there is a multiple occupation for the abroad students, even in Pakistan, in India and Bangladesh. Lot of Bangladesh students studying in Shandong University of Technology in bachelor, and lot of Indian students are working as research scientists and postdoc fellow in Shandong University of Technology. Lot of Pakistan peoples are studying and also working in Shandong University of Technology. There is a lot of interchange the students also available in the Shandong University of Technology for masters and PhD scholars. So if you like, you can find the website and you can apply any of research professor or research institute. You can contact freely. Thank you.
Any questions from your side?
Hello sir, good afternoon sir. Thank you for the wonderful lecture. Usually the entropy changes may cause phase transition. Does the phase transition makes any change in the superconductivity of the material, sir?
High entropy effect is more important for stabilize the phase, because it is not a single component or binary compound. When you form more than 4 or 5 elements with some particular concentration, it should have a different size of atomic size, different type of behavior. So high entropy effect means it should form the single phase. So that's why the change will replica the structure only. But we can't identify this structure will belongs to this, this value belongs to this structure. That we can't predict. The final result only we know. After synthesis, after XRD only we know the results. So we can't predict the structure, but it belongs to only high entropy effect only.
Thank you, sir.
Any more questions? Sir, as far as I know, Superconductors are mainly used in case of MRI, even satellite launching systems, very high technique. And recently I read out that they are going to be used in the next generation fusion reactors.
When you go for the low temperature applications, you used which magnet is suitable. So basically, when you go for the low temperature, NBTI is only the, nowadays the possible way is only NBTI. So these are the alternate method, because in fusion reactor and space application, they are using liquid helium. So liquid helium means these materials are easily to use, but the weight correction should be less. So it may use, but in develop is starting it's starting the period. It's not end. It's starting the period. So when you find it should have some simple structure with very low weight. Why we can't? We can use, but nowadays there is no direct application from this compound. Nowadays it's developed only, but it is very easy to replace commercial superconducting magnets, because the value is close to the NBTI, because we have a reference. When you go for the superconducting magnet, we have a reference with only NBTI magnet only, nowadays itself.
So on the behalf of the Department of Physics in Joseph's College, I wish Dr. Manikandan Krishnan all the very best. Thank you very much, sir, for sharing this.
Thank you, Professor Patrick Prabhu, for leading this session with such grace and efficiency. A heartfelt thanks to our esteemed speaker, Dr. Manikandan Krishnan, for sharing such insightful and inspiring thoughts. We delve into the world of energy storage. The topic, transition metal sulfides for energy storage applications, is crucial in today's world, where efficient energy solutions are a priority for sustainable development. Growth is never by mere chance. It is a result of forces working together. We welcome Dr. Lourdes and Dr. M. Manikandan on the stage for the third session. Here, I gladly invite the chairperson, Dr. S. Lourdes, Assistant Professor of Physics, a man of hard work and teamwork. I now request this chairperson to honor our speaker, Dr. Manikandan, with a memento. Thank you, sir. Now, I kindly invite Dr. Lourdes to chair the session and introduce the speaker.
A very good afternoon, one and all gathered here. A warm welcome you all to this third session of this International Conference on Advanced Materials 2025. It's my great privilege and honor to chair this session. It's really a proud moment for me to welcome our alumnus, Dr. M. Manikandan, a postdoctoral fellow, School of Electronics Engineering, Vellore Institute of Technology, Chennai, who readily accepted our invitation to enlighten us with his talk on transition metal sulfides for energy storage applications. In this wonderful juncture, I am happy to introduce our speaker, Dr. Manikandan. He started his academic journey from a small village, Gobalapuram near Hosur. He moved to Trichy for his undergraduate and postgraduate studies. After that, he joined in Bharadasan University for his MPhil program. After completed the PhD, he joined in different universities, different places. His research interest in supercapacitors and water splitting and CO2 reduction and biosensors. His PhD thesis entitled as Investigation of Electrochemical and Non-Optical Properties of Metal Telluride Nanostructures. And he published more than 16 international journals and 5 articles in progress and 4 conference proceedings. And he attended nearly 25 conferences and presented 8 papers, and also he awarded with the Best Paper Award. And he is joined as a 2020 as a research associate in Rusa Bharatiyar University, and 2021 and postdoctoral fellow in SSN College Research Center, and 2022 he is a postdoctoral fellow in School of Electronics Engineering, Vellore Institute of Technology, Chennai. He filed 2 patents under in the submitted level, and he published 2 book chapters, and he received many awards in his academic excellence, and he is a reviewer of RSC Advances and New Journal of Chemistry and Journal of Inorganic and Organometallic Polymers and Materials, and he acted as an organizing secretary in different programs conducted by the Bharatadasan University. And with these words of introduction, on behalf of the department and management, I wholeheartedly welcome you, sir, for this international conference. Welcome.
Thank you, sir. I am Dr. M. Manigandan, postdoctoral fellow, School of Electronics Engineering, Vellore Institute of Technology, Chennai. Today I am going to speak about transaction metal sulfides for energy storage application. The motivation of the talk is, the world is demand for the renewable energy. Here I have listed some of the countries. In this, India is the 4th place. In 2030, we have a goal to achieve 500 gigawatts. Up to now, we have achieved 203.16 gigawatts from solar, hydro, wind and biomass. To store this energy, we need energy storage device. The energy storage devices are battery and supercapacitor. It is an electrical device. It is a less expansive, lighter and more efficient. It is used in transport vehicles. Central Mechanical Engineering Research Institute, Durgapur, developed graphene oxide, new ultra capacitor for the energy and defense application. CMET, Kerala, is developed carbon aerogel in defense and space sector. Why supercapacitor? It is an energy storage application, the bridge gap between conventional capacitor and battery. Battery possesses high energy density, while in supercapacitor it possesses high power density. And it is a long duration, fast charge, environmental friendly, and the wide temperature voltages vary from 0 to 0.6. It is used in some other applications. Supercapacitor classified into 3 types. One is electric double layer capacitor, pseudo capacitor and hybrid capacitor. In electric double layer capacitor, there is no charge transfer between an electrode and electrolyte. For best example, carbon. It has a large surface area, high chemical mechanical stability and excellent electrical conductivity. Another one is a pseudo capacitor. The Faradic charge transfer between an electrode and electrolyte. It possesses high specific capacitance and high energy density compared to EDLC. The best examples are transition metal oxide and conducting polymers. The third one is an hybrid supercapacitor, the combination of both EDLC and pseudocapacitor. In that itself, there is 3 types. One is symmetric supercapacitor. In symmetric supercapacitor, both anode and cathode act as the same material. In composite hybrid supercapacitor, anode acts as an carbon material and cathode acts as an conducting material, conducting polymers or transition metal sulfides or transition metal oxides. Battery type hybrid supercapacitor. Here, one electrode is acted as a battery electrode and another one is a supercapacitor electrode. Applications of supercapacitor. Nowadays, the supercapacitor used in automotive, that means hybrid vehicles, renewable energy to store the energy from solar and wind, and consume electronics, industrial and aerospace. Transition metal oxide. Transition metal oxide has an high capacitance because RuO2 has a high electrical conductivity and MnO2, nickel oxide, cobalt oxide and ferric oxide has a high specific capacitance. Why RuO2 has high electrical conductivity compared to other materials? It has a fast electron transport leading to a high charge and discharge rates. It shows high pseudocapacitive behavior, and the wide potential window for RuO2 is 0 to 1.4 volt. For other metal oxides, it shows up to 0 to 0.6 volt. By varying the potential for 0 to 1.4 for RuO2 materials, it shows high energy density and is easy to synthesize the metal oxide by using various methods like hydrothermal, salt gel and electrode deposition method. Based on the nanostructures like nanowire, nanorod and nanoparticles, it provides a large surface area and enhance the electrochemical performance. Transition metal sulfides. Compared to transition metal oxide, transition metal sulfide shows high electrical conductivity. For example, molybdenum sulfide, cobalt sulfide, nickel sulfide and ferrous sulfide. It shows high capacitance compared to transition metal oxides. The higher theoretical capacitance is higher for transition metal sulfides compared to transition metal oxides. The challenge with the transition metal oxide, it shows high cyclic stability with the synthesis complexity and the electrolyte compatibility. The further directions to overcome the challenges are composite material, that is transition metal sulfides with the carbon-based materials to enhance the stability and electrical conductivity. The nanostructuring means to developing the nanostructures of transition metal sulfides to maximize the surface area and the active sites. Cyclic voltammetry. It is an electrochemical technique which allows the redox and transport properties of the given system in a solution. Here we have used 3 electrode system. One is a counter electrode, and another is a reference electrode, and another one is a working electrode. Here the working electrode is a nickel foam, and the reference electrode is an AgCl, and counter electrode is a platinum wire. Here we have used electrolyte as an acid or alkaline. The charge and discharge. It is a chronopotentiometric method. It supports the electrolyte between the initial potential to the final potential at a particular current density. The functions for battery and supercapacitor, we have listed some of the functions. In this, the cycle life is high compared to battery for supercapacitor. The service life also high compared to battery for supercapacitor. Here the energy density is high for a battery and low for supercapacitor, and the power density is high compared to battery for supercapacitance. The efficiency also higher for supercapacitors. Based on this Ragon plot, we have identified which material is suitable for a supercapacitor or battery based materials. Here I have going to discuss my research work, that is an R represents the reduced graphene oxide and the zinc cobalt sulfur through hydrothermal synthesis. Here I have taken graphene oxide and sonicate it for 2 hours, and then we have added zinc cobalt and urea and thiourea for a sulfur source, and we have kept oven at 150 degrees Celsius for 15 hours, and finally we have obtained the nanoparticles. To confirm the material, we have characterized the XRD. The JCPDS card number is well matched with the XRD plane. This is the Raman. To confirm the carbon-based material, we have took the Raman. There is a D and G band. The D band is around 1317 and the G band is around 1586. To confirm the surface area of the material, we have characterized the bed application. This is the SEM image. The prepared materials have characterized from SEM. The particle size of the material is 60 to 70 nanometers. This is the TEM image, and this is the TEM images, and this is the elemental mapping. The color represents the materials. The XPS. Here we have confirmed the binding energy of the materials. For example, this is the zinc source 2p 1/2 and 2p 3/2 at the electron volt of 1022 and 1045 electron volt. This is in a cobalt, the conformation of sulfur and carbon. The electrode preparation for the supercapacitor. Here we have taken nickel foam as an working electrode. In this 2 x 1 centimeter, we have coated 1 x 1 centimeter. The prepared material is taken as an 75% and 15% of activated carbon to enhance the conductivity of the material, and we have taken 5% of PVDF as a binder, and we have added few drop of NMP to become it as a paste, and we have coated using Dr. plate method, and this is a 2 electrode device. For this M plus divided by M minus is equal to C minus divided by C plus. M plus and M represents the working material and C represents the carbon based material. From that we have calculated the weight percentage and we have coated the material in the nickel foam and we have fabricated the device as an anode and cathode. This is the CV. Here we have fixed the potential from 0 to 0.6 volt and we vary the different scan rate from 10 to 50. Why we are varying the scan rate means at the 10 millivolt per second there is an interaction between electrode and electrolyte. So it will take time and we source the oxidation and reduction peaks. This is the charge and discharge graph. Here we will fix the potential from 0 to 0.6 and we vary the different current density. From this we have calculated the specific capacitance by using this formula CSP is equal to I into del T divided by M into del V, where I is the discharging current and del T is the discharging time, del V is the potential window and M is the active mass. Thus I is the current density, what we given here, the 1, 2, 3, 4 we are varying, no, that is the high values, and the del T represents the T2 minus T1 value. We have to subtract this value and we have taken as an del T value, and M is the mass load, the electrode, in the electrode how much material we have coated, that is an M, and del V is the potential, that is 0.6 volt. By using this formula we have calculated the specific capacitance. While the current density increases, the specific capacitance value decreases because at the low current density there is an interrelation between electrode and electrolyte. The asymmetric device, that is a 2 electrode device. In asymmetric, anode acts as an RZCS and cathode acts as an RGO. For this we have varied the different potential from 0.8 to 1.6 volt. Up to this the material is stable. After that we fixed the 1.6 volt fixed the 1.6 volt potential and we vary the different scan rate. For the GCD also we have varied the different potential. It's stable up to 1.6. We have fixed the 1.6 volt and we vary the scan rate. Based on this we have calculated the capacitance, super capacitance by using that formula. Here we have achieved 181 for one current density and we have run the stability up to 10,000 cycle. The capacitance retentions of the material shows 92% and the coulombic efficiency is 98%. And we have did EAS for the prepared material. This is the RS source 0.18 volt ohms and RCT is an 1.1 ohms. Based on this RCT, the RCT value is very low, means the material has the high conductivity, and this is the energy density and the power density graph. E is equal to CV square divided by 7.2 is the energy density, and power density is P is equal to E into 3600 divided by T. Here we have already calculated the CV square. The CV is the capacitance value divided by 7.2. The energy density decreases while power density increases. This is the another one what R represents RGO and manganese cobalt sulfur through the hydrothermal synthesis, and this paper is published in scientific report. The same basic characterizations and from the CV, GCD and all shown here. The third material is a combination of both zinc, manganese, cobalt, sulfur through hydrothermal synthesis. This paper published in Physica Scripta. Here I have compared some other reported literature and the synthesized materials. In this, magnet, cobalt, sulfurs shows high cyclic stability up to 97% for 10,000 cycles. The another one work is an mexine. Now mexine is a hot materials to work on the energy applications. It is a new class of 2 dimensions transition metal carbonides. That is the combination of the M represents the transition metal and the X represents the carbon or nitrogen, and the TX represents the OH oxidation on fluoride. The combination of both three we will we will prepare the mixine and the metal organic framework. Metal organic framework means metal with some other ligands. With the combination, we will prepare the metal organic framework. Mixine shows high electrical conductivity. It is a fast electron transport. It shows high surface area, high capacitance, and the fast ion transport, chemical stability, and tunable surface chemistry. The MOF shows high surface area compared to mixine. So we have here we have listed some of the properties for mixine, carbon-based material, metal oxide, and metal sulfide. In this, mixine shows high conductivity, and the capacitance value is also high compared to all other three materials. So for this work, I have chosen mixine. Here, titanium, aluminum, carbide we have taken, and we have etched through HF for 2 days with the RPM of 700 RPM. At the time, the aluminum get evaporated, and we have obtained the titanium carbide TX. In this, we have added zinc MOF, and finally, we have obtained MXOF. That is the combination of mixine and metal organic framework. We have confirmed the XRD through the JCPDS value. The bed surface shows the surface area and pore diameter. For the composite materials, it shows high surface area, that is 1132 meter square per gram inverse. This is the epitome of the mixine. It shows the layer structure, and this is the MOF. It shows in a cubic hexagonal structure. The XPS, it confirms the titanium, zinc, carbon, and oxygen. This is the CV studies. Here also we have varied the different scan rate and different current density, and we have calculated the specific capacitance. For this composite shows high capacitance of 1788 for a current density of 1, and it shows the capacitance resistance of 100% for up to a 5000 cycle. Based on these three materials, composite shows high capacitance. So we have taken the material for an 2 electrode devices. Here also we have varied the potential from 0.8 to 1.6 volt for CV and GCD, and we have calculated the specific capacitance using that formula, and we have tabulated the figures. This material shows the capacitance resistance of 91% up to 10,000 cycle with the Coulombic efficiency of 98%. From EAS, we have seen the RCT is 4.3. It is very low, so the material is shows high electrical conductivity. We have calculated the energy density and power density also. The material shows high energy density of 64 and power density of 800. Here we have synthesized RZN COS, MCOS, and ZMCOS with the composite of RGO through hydrothermal method. The XRD shows the confirmation of the prepared materials. The epicenter was confirmed the presence of nanoparticles. The specification of the prepared electrodes are listed here, and RMCS shows the high capacitance of 1925 compared to other two materials. The fabricated device displays an high energy density of 64 for the RMCS element, and we synthesized mixine, MOF, and MXOF. It shows the epicenter shows the nanosheet layer for mixine, hexagonal structure for MOF, and hexagonal cubic for MXOF. In this MXOF shows high capacitance of 1788. So we have fabricated the device for MXOF, and it shows the high energy density of 64 watt-hour per kilogram. These are the references. Acknowledgement. I wish to thank VIT for providing funding for my postdoc fellow, and I thank Dr. E. Manigandan as the supervisor, and I thank Syed Abu Dahir. He is the student for me. He helped for the synthesis, and I thank Micro and Nanolob for providing the facilities for synthesis, and the Center for Advanced Material and Innovative Technologies for providing the facilities, and I thank the Department of Physics, St. Joseph College, Trichy. There is an intake for PhD in July section. They are providing 3 years fellowship, For first year, they are giving 31,000, and the second year, third year, they are giving 35,000. If those who want to do PhD in VIT, you go and search the website and apply. The last date is 31 March, and there is an entrance exam on 20 and 24. From that, they will shortlist and they will be conducting an interview. After that, you join as a PhD there. Thank you.
Thank you, Dr. Manikandan, for your nice presentation. Audience, from your side, any questions?
Good afternoon, sir. Actually, currently I am doing some work in hybrid supercapacitors, sir. While combining lot of materials, it may cause some compatibility issues there. How can we overcome that compatibility issues in hybrid supercapacitors?
So what type of materials you are working?
I'm sulfides. Currently, I'm going with alkalides.
Material name I'm asking.
NiCr2S4.
NiCr2S4. Nickel shows high conductivity, but chromium doesn't show that much of conductivity. So the material shows only less cyclic stability only.
Yes. How can we choose that?
Based on the conductivity, you have to choose the materials.
Okay, sir. Thank you, sir.
Any other questions? If you don't have any questions, we please wind up the session. And thank you, Dr. Manikandan, for your wonderful presentation and a nice interaction. Thank you all for your participants, active participants.
Thank you, Dr. Lourdes, for your proficient guidance in this session. A special thanks to our esteemed speaker, Dr. Manikandan, for your sharing valuable knowledge and expertise.
An announcement for the oral and poster presenters. The venue for the oral and poster presentation are pasted at the registration desk. Kindly note the venue and your abstract number now itself. At 3:30, the poster presenters can hang their posters at the allotted venue. Let us break for lunch and come back at 2 p.m. sharp. The lunch will be served at KP Joseph Hall for the PG students and research scholars. Come back at 2 p.m. sharp.
Sir Veerappan sir?
I'm audible தான் சார் கேட்குது நீங்கள் பேசுறது.
Yes sir.
பட் என்னோட வீடியோ ஓகே இப்போ வீடியோ ஆன் பண்ண முடியுது. ஓகே தான்.
Yeah, we can spotlight like this.
Right.
Okay.
Right. Do you want to see the presentation slide or just it's fine?
Yeah, sure. However.
Okay. Okay. Shall we wait for 7 more minutes?
Yes sir. Yes sir. People are gone to lunch. They are on the way.
Okay. Okay. I'm ready here. Just let me know when I want to.
Sure sir. It's evening in the evening for no. It's morning.
It's morning, 8:30.
Yeah. Good morning.
8:30. Good morning. Yeah. சரி ஓகே சார். நான் வீடியோவில் அது பண்ணிக்கிறேன், கண்டினியூ பண்ணிக்கிறேன்.
சார் ஜான்சன் பேசுகிறேன். நல்லா இருக்கீங்களா?
நல்லா இருக்கேன் சார். நீங்கள் எப்படி இருக்கீங்க?
எங்க அங்கே வரணுமா?
அது கேமரா ஆன் பண்ணல, ஆஃப் பண்ணிருக்கோம். இங்க உட்காருங்க, இங்க உட்காருங்க. ஓகே சார், அங்கேயே உட்காருங்க, பரவாயில்ல. எனிவேஸ்
சார் மூஞ்சி தெரியுதா? மூஞ்சி
தெரியுது தெரியுது சார்.
ஓகே சார், ஓகே சார். எனக்கு குரல் மட்டும் தான் அதே மாதிரி நினைச்சா ஆளும் அப்படியே இருக்கீங்க.
ஆமாம்மா, வெரி சிமிலராக தான் இருப்போம்.
ஆமாம். ஓகே, கிரேட். இப்போ லஞ்ச் பிரேக் ஒரு 5 மினிட்ஸில் அசம்பிள் ஆகிடுவாங்க ஆடியன்ஸு.
ஓகே ஓகே, நோ ப்ராப்ளம் நோ ப்ராப்ளம்.
2 o'clock ஷார்ப் ஆரம்பிச்சிடலாம்.
ஓகே சார், ஓகே.
ஓகே,
நோ வரிஸ் நோ வரிஸ்.
தேங்க்யூ தேங்க்யூ
தேங்க்யூ சார். சரி, இது ஆக்சுவலி நீங்கள் ஃபிசிக்ஸ் டிபார்ட்மெண்ட்டா கெமிஸ்ட்ரி? அது ஃபிசிக்ஸ். ஓ ஓகே ஓகே. நான் ஒரு டைம் கெமிஸ்ட்ரி டிபார்ட்மெண்ட் விசிட் பண்ணியிருக்கிறேன் டாக் கொடுக்க. எப்போ மேபி ஒரு 7-8 வருஷத்துக்கு முன்னால் இருக்கும்னு நினைக்கிறேன்.
மேபி
கெமிஸ்ட்ரியில். அதுக்கப்புறம் ரொம்ப நாள் ஆச்சு இந்த பக்கம் வந்து.
வாங்க, ஊருக்கு வருவீங்கல்ல?
ஆமாம்மா, வருவோம் சார். பட் வரும்போது பெரும்பாலும் பர்சனல் கமிட்மெண்ட்ஸ்லேயே நான் போயிடுவேன். தம்பி தான் நிறையா போய் டாக் கொடுப்பாப்ல ஊருக்கு வரும்போது. பட் நான் அவ்வளோவா
ஜஸ்ட் ட்ராப் மீ an email so that we can be in touch. அதான் வாட்ஸ்அப்பில் இருக்கும்ல.
ஓகே ஓகே சார். மேபி நெக்ஸ்ட் டைம் வரும்போது கண்டிப்பாக வரேன். திருச்சி
சம்மரில் தான் மோஸ்ட் ப்ராபப்லி வில் கம் இல்லையா?
மோஸ்ட் ப்ராபப்ளி சம்மரில் தான் சார். அங்கே இருக்கிற வரைக்கும் இப்போ மேபி அதை நான் ஷிஃப்ட் பண்ணலான்னு இருக்கிறேன் டிசம்பருக்கு. இங்கே டிசம்பர் ரொம்ப கோல்டு,
ரொம்ப குளிராக இருக்கும். ஆமாம்,
அதனால மேபி கிறிஸ்மஸ் டைமில் டிசம்பர் அங்கே இந்தியா வந்து
கிறிஸ்மஸ் will be a pleasant one year. ஓகே ஓகே. ரொம்ப வின்டர் கடுமையாக இருக்கும். ஓகே,
வின்டர்லாம் இருக்கும். பட் ஆக்சுவலி அந்த டைமில் தான் ரொம்ப பியூட்டிஃபுல்லாக இருக்கும் இங்கே எல்லாமே.
லைட்ஸ் எல்லாம் போட்டு டெக்கரேட் பண்ணி பயங்கரமாக இருக்கும். ரொம்ப கிராண்டாக இருக்கும்.
ரொம்ப கிராண்டா ஒரு 2 மாசம் அப்படி இருக்கும்.
ஆமா, டிசம்பர் 1ஆம் தேதி ஆரம்பிச்சிருவாங்களே ஃபுல்லாவே.
அது நவம்பர்லயே ஆரம்பிச்சிருவாங்க.
அது ஜனவரி வரைக்கும் அப்படியே தான் இருக்கும்.
ஆமா, ஜனவரி 15 வரைக்கும், 10-15 வரைக்குமே அப்படிதான் இருக்கும்.
கிறிஸ்மஸ் மார்க்கெட்லாம் வேற போடுவாங்க,
நிறைய மார்க்கெட். ஆமா, இங்க கிளாஸ்கோ மார்க்கெட், அப்புறம் எடின்பரோ மார்க்கெட் நல்லா இருக்கும் பக்கம்.
எல்லாம் டிஸ்கவுண்ட் சேல் எல்லாம் போடுவாங்களே, டிஸ்கவுண்ட் சேல்
நிறைய சேல் இருக்கும். ஓகே சார், ஓகே. ஒரு தம்பி டாக் முடிச்சுட்டா கொடுத்தாரா? நான் பேசி கொஞ்ச நாள் ஆகுது, ரீசெண்டாக பேசல. கோவிந்த்
கொஞ்சம் பிஸியாக இருக்காரு.
கோவிந்த் டாக் இல்லையோ? ஓகே ஓகே. நானும் பேசி ஒரு வீக்ஸ் ஆகும்னு நினைக்கிறேன். பேசலாம்,
கொஞ்சம் பிஸியாக இருக்காரு, அதனால் விட்டாச்சு.
ஓகே ஓகே.
அவங்க நேரில் தான் வருவோன்ற ஒரு உறுதியான முடிவோடு இருக்காங்க.
ஓகே, நைஸ்.
மேபி நெக்ஸ்ட் இயர் பாசிபிள்.
ஓகே.
சவுத் கொரியாவிலேருந்து 2 பேர் வாரேன் நாங்கள். சவுத் கொரியாவில் அவங்களுக்கு இந்த லூனார் இயராம ஏதோ செலிப்ரேஷன் இருக்கு, பிக் செலிப்ரேஷன்ஸ்.
ஓகே ஓகே. அந்த ரீஜன்ல இப்போ சைனீஸ் நியூ இயர் இருக்கும். அப்போ
எஸ் அதனால எல்லாருமே அவுட் ஆஃப் ஸ்டேஷன் இருப்பாங்க. உங்களுக்கு ஹோம் டவுன்ல இருக்க மாட்டாங்க. உங்களுக்கு ஒரு மாதிரி செலிப்ரேஷன்.
ஆமாமா. இந்த சீசன்ல மேபி அங்க வந்து
எனக்கு
எல்லாம்
என் ஃப்ரெண்டே
வெக்கேஷன்
ஒருத்தர்
போயிருப்பான்.
என் ஃப்ரெண்டே ஒருத்தர் இருக்காரு சவுத் கொரியாவில், சுக்வான்.
ம்.
பட் அவர்
ஓகே.
சார் அவுட் ஆஃப் ஸ்டேஷனில் இருப்பேனே கண்ணா முன்னான்னு அப்படின்னாரு.
ம்.
அப்போ சரி ஓகே பரவாயில்ல. நான் ஒரு முதல்ல வரேனாரு, நேரில் கூட வரேனாரு. அப்புறமாட்டுக்கு
ம்.
கொஞ்சம் ஒரு 20 நாள் தள்ளி இருந்தா வந்திருப்பேன் அப்படின்னாரு. பிப்ரவரி
ஓகே.
20க்கு மேலன்னா வந்திருப்பேன் அப்படின்னாரு.
ம்.
எனக்கு இந்த
ஆமா, அங்க வந்து இது ஒரு சீசன் டைம் தான். எல்லாருமே இருக்கிற சீசன்.
சவுத் கொரியா, அந்த தாய்வான், அந்த சைனா, அந்த ரீஜன் எல்லாமே அந்த செலிப்ரேஷன் இருப்பாங்க பாருக்கு. ஹாங்காங்
ஆமாமா.
ஹாங்காங்கு எல்லாமே அந்த
ஓகே.
புறமே. இந்த ஐடியா எனக்கு தெரியல முதல்ல. சரி ரைட் ஓகே.
ஆமாமா.
அங்க
அவங்க ஃபுல்லாவே அது ஒரு பெரிய
ஈவன் வெஸ்டர்னுமே வந்து இப்போதான் கிறிஸ்மஸ்லேருந்து வந்திருப்பாங்க. ஜனவரி 15 தான் வந்திருப்பாங்க.
இங்கெல்லாம் வந்து ஆல்மோஸ்ட் இங்க குயிக்கா ஆரம்பிச்சிருச்சு சார். நான் மற்ற கண்ட்ரீஸ்லாம் பார்த்தீங்கன்னா, ஒரு ஒரு டெட்லைன் ஒரு ஒரு 2, 3 நாள் தள்ளி ஆரம்பிக்கும். இங்க வந்து பன் அ 10, 12 ஆரம்பிக்குன்னா டக்குன்னு ஆரம்பிச்சுரும்.
ஆரம்பிச்சிடும்.
அவ்வளோதான். கைண்ட் ஆஃப் இங்க ஒர்க்கிங் கல்ச்சரே வந்து
ஜெர்மனி ஃப்ரான்ஸ்லாம் லேட் ஆகுது சார். 15-20 தேதி ஆகுதுல்ல ஜெர்மனி.
ம். மேபி மற்ற ப்ரொஃபஷன் எப்படின்னு தெரில. அகாடமிக்கை பொறுத்த வரைக்கும் நாங்க 7, 8ல இருந்தே எங்களுக்கு ஆரம்பிச்சிருச்சு.
ஆரம்பிச்சிருச்சு. ஓகே ஓகே.
ம்.
ஆனால் ப்ரொஃபஸர்ஸ் கொஞ்சம் லீவ்லேயே இருப்பாங்க போல இருக்கு இல்லை? அப்படி இல்லையா?
டீச்சிங் ப்ரொஃபசர்ஸ் வந்து கொஞ்சம் டைம் லீவ் எடுத்துப்பாங்க. ஏன்னா இதை தாண்டிச்சுன்னா அவங்களுக்கு வேற எங்கேயுமே லீவ் ஆப்ஷன் இருக்காது. இப்போ ரிசர்ச் பண்றவங்க எங்களுக்கு இப்போ
அதாவது
ஒரு
லேப்லாம் திறந்துருவாங்க போல இருக்கு. இந்த ப்ரொஃபஸர்ஸ் எங்கேயாவது கொஞ்சம் அவுட்டிங்ல அங்கே இருப்பாங்க போல இருக்கு.
அவங்க ஏதாவது அர்லி வெக்கேஷன் இந்த டைம்ல தூக்கி போட்டுட்டு பேலன்ஸ் பண்ணிப்பாங்க.
ஜனவரி 20க்கு மேலே தான் ஒருத்தராக வருவாங்க போல இருக்கு. நான் யூகே வந்ததில்ல.
ஓகே.
நான் வந்து பெல்ஜியத்துக்கு
ஸ்ட்ராத்கிளைட்லாம் பார்த்தீங்கன்னா ரொம்ப பிஸியான யூனிவர்சிட்டி, பயங்கர பிஸியான யூனிவர்சிட்டி.
பெல்ஜியத்தில் இருந்தேன், லூவன்ல.
ஓகே ஓகே ஓகே.
லூவன்ல 2012ல இருந்தேன்.
ஓகே ஓகே.
லூவன்லையும் ட்ரஸ்டன்லையும் இருந்தேன் 3 மாசம்.
கேயூ லீவன் இல்லைங்களா?
கேயூ லூவன்லையும் மேக்ஸ் பிளாங்க் ட்ரஸ்டன்லையும் இருந்தேன். எராஸ்மஸ் நேனா அவார்டு, விசிட்டிங் அவார்டு 3 months. அப்புறம் 2016 to 17 இன்சால ஒர்க் பண்ணேன் 1 year. இன்சா ப்ளூவா பிரான்ஸ் இருக்குல்ல, அங்கே எனர்ஜி ப்ரோக்ராமுடைய கோஆர்டினேட்டராக இருந்தேன் 1 year.
ஓகே ஓகே. ஓ சரிங்க சார்.
நான் போஸ்டாக் அங்கே தான் பண்ணேன்.
இந்த பக்கம்
போஸ்டாக் வந்து யூனிவர்சிட்டி ஆஃப் கோயம்புரால பண்ணேன், போர்ச்சுகல்.
ஓகே. ஸோ யூரோப் ஃபுல்லாக சுற்றிருக்கிறீங்க.
ஆமாம். அதனால் ஸ்பெயினில் கொஞ்ச நாள் இருந்தேன், அந்த சரகோசா யூனிவர்சிட்டியில். அங்கே கொலாபரேட்டர் இருக்கார் ஜோஸ் வீரியேட்டானு, அங்கே கொஞ்ச நாள் இருந்தேன். அது மாதிரி ஒரு 4-5 ட்ரிப்பு வந்திருக்கேன். கொஞ்சம் ஃபேமிலி கமிஷனால வந்துட்டு திரும்ப போகலான்னு நினச்சேன். திரும்ப வரதுக்குள்ள கொரோனா வந்து நம்மளை பிடிச்சி வச்சிருச்சு. அப்போ அப்படியே ஃப்ளாட் ஆகியாச்சு. திஸ் இஸ் த டைம் ஃபார் மீ டு ஃப்ளை அகைன்.
கண்டிப்பாக வாங்க.
மேபி see you next year.
பார்ப்போம் இந்த பக்கம்.
ஓகே, ஐ ஹோப் த ஸ்டூடெண்ட்ஸ் வில் கம் soon.
ஓகே. நோ, லன்ச் டைம் வந்து ஜென்ரலாக நான் டாக்குக்கு ப்ரிஃபர் பண்ணுறதில்ல. ஏர்லி மார்னிங் தான் ப்ரிஃபர் பண்ணுவேன். பட் இந்த டைம்னால என்னால் மேனேஜ் பண்ண முடியல.
ஓகே. ஆன் பண்ணிடுங்க ஸ்டூடெண்ட்ஸா.
Check.
So just let me know when you want me to start.
Sure, sir. Yeah, we'll start in a minute or two, sir.
Okay, just let me know. Yeah.
Once again, on the behalf of the Department of Physics, St. Joseph College, I welcome you all back to the International Conference on the Advanced Materials. The laws of physics apply to every heartbeat, every neuron, every cell. Moving forward to the next session, I would like to welcome Dr. P. Ganikiraj, Associate Professor of Physics, St. Joseph College, to chair the session on next generation of electrochemical diagnostic device technologies for cardiovascular disease by Professor Veerappan Mani.
Respected resource person, Dr. Veerappan Mani, my dear participants, good afternoon. Since this is a AC hall, therefore you may not be difficult after having good lunch. So let me introduce Dr. Veerappan Mani for his inspiring talk, highly technical talk, namely next generation of electrochemical diagnostic device technologies for cardiovascular disease. My dear friends, you know, so far we don't have any measuring device to understand the biomarkers in the blood, unless otherwise if it is taken as a sample. So here comes a new generation device which can be weared by everybody. So without taking any blood sample, we can understand different biomarkers present in the blood so that the cardiovascular disease symptoms can be understandable and which is very much useful to diagnose and medication. So this Professor Dr. Veerappan Mani have a wonderful experience, very rich experience in this field. He has finished his BSc Chemistry from Periyar University, MSc Chemistry from Bharatidasan University. Then afterwards he moved on to abroad, PhD Chemistry, National Taipei University, Taiwan. Then higher education teaching certificate from Harvard University, United States. Then PG certificate teaching degree, University of Strathclyde, Glasgow, United Kingdom. Veerappan Mani is a Senior Research Scientist at the Center for Advanced Measurement Research and Health Translation, University of Strathclyde, Glasgow, United Kingdom. He has completed his PhD from the National Taipei University of Technology, Taiwan. He also received many awards, in which the highlighted award is the 2023 Rising Star in Measurement Science and UK Global Talent Visa recipient, and he is a world's top 2% scientist. So such an eminent scientist is going to deliver a lecture in a remarkable device. He has a rich professional experience from various universities, including United Kingdom, United States, California, and so on. He has a good teaching experience from various universities, including Taiwan, Japan, and United Kingdom. His research interest is electrochemical sensors and biosensors, electroanalysis, 2D materials, bioengineering, nanomaterials, nanostructured electrochemical interfaces, material science and engineering, biomedical diagnostic devices. He is an editorial member in various reputed journals. He is also a member of various professional bodies like American Chemical Society, Royal Society of Chemistry, and so on. He has reviewed more than 300 indexed papers so far. He also received many research grants in terms of crores of rupees from various bodies. So on behalf of all of us gathered here and on behalf of our management and our own department, I welcome Dr. Veerappan Mani wholeheartedly to deliver this lecture. Welcome, sir.
Thank you, sir. Thank you. I hope my voice is audible to the...
Yes,
Okay.
yes, your voice is audible.
Great. Thank you so much for a very brief, very detailed introduction, and I'm glad to be part of this wonderful event. Today I'll be talking about my research and some of my colleagues' research on next generation electrochemical diagnostic technologies for cardiovascular disease. So let me begin from the cardiovascular disease impact, and it's commonly known as heart disease. And almost all of us are aware the term heart attack by some means through our relatives or through our friends, families, and so on. And it's very vaguely termed as heart attack, although heart attack is a very vague term and it's a very complex disease actually. But let's see the number of fatalities each year from the cardiovascular disease. On the left-hand side of this presentation slide, you will see a chart that's showing how many people are dying every year due to various diseases. And you see cardiovascular disease is the number one in the chart. It kills 17.8 million people in 2016. It's like 10 years ago. And by around 2020, the number goes to 21 million. And it is estimated to be close to 25 million by 2030. So it's a really, really serious problem. It is an epidemic. And in fact, you see together all other diseases contribute like 50%, and just heart disease contribute 50% of the fatalities each year. And you could imagine how much economic burden cardiovascular disease put on each country's healthcare budget. Unfortunately, cardiovascular disease is so complex, it's really challenging for the early diagnostics. And mostly we just know heart attack. However, as I mentioned, it's a very vague term. There are a lot of disease with heart disease. The most common one is coronary artery disease that we see as like a plug in the artery or some kind of blockages in the artery. That's the most common one. However, there are others like pericarditis, cardiomyopathy, heart valve disease, to name a few, but there are more than 50 or even a lot of different varieties of disease that has to be taken considered. And each disease is specific to certain stuff. There could be some problem with the valves, or there could be some problem with the chambers, and there could be some problem with the vessels. So it require very accurate and also early diagnostics. And the most important problem in cardiovascular disease is early diagnostics. Not only in cardiovascular disease, let's say all other chronic diseases which don't show signs and symptoms in the early stage. That's the biggest challenges in cancer. Let's say other example. But we talk about infectious diseases like COVID or any kind of viral bacterial infections. They show signs and symptoms in the early stages. So within 10 days or 15 days, most of the times, although some of them are asymptomatic. And anyhow, you can detect such diseases earlier, but these kind of diseases termed as chronic diseases, they don't show any signs and symptoms in the early stage. The person may have the disease for 10 years or more than 10 years without knowing that, and suddenly they will get a problem. Let me give you a brief idea about how are we currently diagnostics cardiovascular diseases in the hospital. So this slide will give you an overview about the current medical practice. So let's say if a person has some physical symptoms of heart problem like chest pain or shoulder pain or like fast heart beating, then the patient go to the hospital, then the doctor do the stethoscope testing, check the heartbeat, and then recommend ECG or EKG testings. And after that, recommended chest X-ray, CT scan, echo, and followingly blood test, mostly ELISA. But you see, so much expensive, all these techniques together, cumulatively, they cost a lot of money for a particular patient. And also it's time consuming. It takes like more than 5 to 6 hours time. And the other thing is, many patients who may not have heart-related diseases may end up having similar symptoms. So if we do all these diagnostics for those people, we are just wasting the money, right? So what we need is a very low-cost, simple, user-friendly diagnostics devices in all these areas. And my research is mostly about blood test and ELISA. ELISA is the most standard gold assay method currently used in the hospital. Unfortunately, this is like 3 to 4 hours of time it requires, and it requires a very highly skilled technical person. And generally, they collect the samples and then they do serum collection. Followingly, they do a lot of solutions, pipetting, washings, capture antibody, detection antibody. So it's so many steps. So what is urgently needed in the healthcare sector to tackle cardiovascular disease diagnostics is we really need a user-friendly, simple diagnostic device that can directly quantify blood biomarkers directly from the whole blood. Doesn't require the serum preparation. So such a user-friendly, simple device is really needed. And in terms of accuracy, it doesn't require 100% accuracy in the first place. It's fine to have 80% accuracy, but we really need a quicker assessment so that we can choose who are the patients really need care. Then we can send them for the other tests like more expensive scans like X-ray or CT scan. So that's the thing. And in fact, in UK, and there is the assessment by just having these kind of diagnostics devices, the healthcare can save billions of money, I should say. That's a very big paradigm shift if we have such a devices. And That's at the same time is more complicated and challenging to have these devices. Why? Why it's really complicated to make such a sensitive device? Because these blood biomarkers are so low in the blood samples. We are talking about a nanogram per ml. Cardiac troponin I, in this table you see on the left hand side, I show you the name of the some of the cardiac biomarkers: troponin I, troponin T, BNP, BNPT, CRP, and so on. What will happen if a person has some kind of heart-related diseases or heart attack, let's say AMI in technical terms? The person's heart releases these chemicals into the bloodstream. So what we do, we have to detect those cardiac biomarkers using our biosensor devices. And such a low concentration, it's really challenging to make such a simple devices. That's why we have to use a lot of washings, pipettings, ELISA to capture them. And there are a lot of cardiac markers, like more than 15 direct markers, and we also have add-on markers. And I'm pretty much sure in the future we will have more number of cardiac biomarkers as more intense discoveries are happening in this field. Right. Let me bring electrochemical technologies. Why I believe electrochemical technologies are a good fit to develop diagnostic devices for cardiovascular biomarkers. So the technologies have three key important properties. The first thing is it's portable and handheld. If you see the right hand image, the one which shows a finger prick blood with a glucometer, that's something most of you quite familiar with. That people who are diabetics, they use such a small glucometer to measure the presence of glucose, how much glucose is there, and then based on that reading they take an insulin injection. And you see, this device is so simple that anyone can use. You don't need any kind of technical knowledge. All you need is just a finger prick, a drop or two drops of blood, place the blood on the sensing zone of the electrode, connect the electrode to the meter, and you get the number. Then you know what to do, whether to take insulin or not. So very such a simple system, and we need such a simple and user-friendly diagnostic device for cardiovascular diseases. The good thing from diabetes is the glucose concentration is really high in the millimolar concentration, and we have a fantastic enzyme known as glucose oxidase. So it's easy to make glucose biosensor. So we are producing billions of glucose biosensor devices. However, as I mentioned in the previous slides, cardiovascular markers concentrations are pretty low, very low. So that's the most important challenging. And these are proteins. These are not metabolites. So when you have proteins, it's really, really challenging to make a electrocatalytic biosensor like enzymatic biosensor. We have to do affinity-based biosensors like antibodies, aptamers, DNAs, and so on. And that brings other complexities. However, electrochemical technologies are fantastic signal readouts. They're quite friendly, and it's a completely electronic technology, meaning they don't depend upon the sample's turbidity. Unlike optical methods, you need a serum. For electrochemical technologies, you just use a whole blood. It's a direct digital signal conversion. And also, you could convert these electrochemical technologies into wearables, implantable, and integration, as Professor mentioned in the previous talk. These have a potential capacity to be a wearable sensor. So in future, we could have a wearable cardiac biosensor, wearable ECG, wearable biosensor that detect cardiac markers present in the sweat. It has such potential. And also, it has the potential to shift the diagnostics from lab to home. That's really, really necessary because at the moment, hospitals are always overwhelmed with huge number of patients. So imagine if we have a device that a patient can use at home and able to transfer the data to the doctors, and doctor can do medication or medical intervention from the hospital and patient attend that from the home. That really, really save a lot of money and healthcare burden, ease healthcare burden. Right. So let me quickly give you my research in a nutshell. Is my vision is to improve heart health for all through the diagnostic devices that I make. And in today's talk, I will walk you through these three key areas of my development. The first one is electrodes and materials. Second one is bioreceptors and biosensors. Third one is diagnostics and integration. And you see, this is a completely interdisciplinary topic. By college training and master's training, I'm a chemist, and then later I learned biochemistry and then becoming bioengineering and surface science. It requires expertise from all the areas, and therefore it also requires intensive collaboration among other cross-disciplinaries working along with a different team. So I use all the time the term we, sometime I, because many of these works are done as a team. All right, so let me give you introduction for each of these three sections. So my subsequent lecture will be categorized into these three areas. For each area, I will introduce their importance, why that area requires development, and then I'll show some of my research results wherever necessary from others' research. And finally, let's see the conclusion. Right. So the first area I'm gonna take is electrodes and materials. I'll talk about what are the type of materials I have developed, mostly laser-induced graphene electrode, although screen printing carbon electrodes or screen printing gold electrodes are quite popular, and materials like graphene or other 2D materials, vaccines, and so on. And in the second chapter, bioreceptors and biosensors. What are the bioreceptors are commonly used in this field? How biofunctionalization is performed by this area. That's a very, very challenging area, biofunctionalization. How to connect the bioreceptors world to the electronics world. So it's like bridging the living world and the dead world. Dead world means I'm talking about electronics world that communicate language through electrons, and biological worlds talk to each other through ions, mostly like protons, calcium, and ion pumps. So biological world talks in terms of ionic currency or ionic language. The electronic world communicate through electrons, and biosensor device is nothing but bridging these two worlds together. As a result, we will end up having a fantastic electrochemical sensor devices that help us to measure these cardiac biomarkers, and we need a lot of strategies there. I'll talk about that. And in the third part, I talk about diagnostics and integration, mostly electrochemical diagnostics technologies like differential pulse oximetry, electrochemical impedance spectroscopy, square wave oximetry, basically playing around different parameters of electronics. And also I briefly talk about some of the integrated diagnostic device that developed from my lab, how to integrate multiple systems together, a reader, electrode, smartphone, IoT, such stuffs. Right, let me bring the electrodes. These electrodes are kind of printed electrodes. So when I started my PhD journey, it was like making materials deposit on the electrode. But later I realized for a commercial or industry scale applications, we need a printing technology, because printing technology allows you a mass producible roll-to-roll back printing, right? Like even our dresses or all the big revolutions happens in printing technology. So then I thought these laser-induced technology could be the best one, and it was started just 5-6 years ago. Now quite popular. Most of the people using these electrodes, and over the 5-6 years, I made a lot of LIG electrodes, not only for cardiovascular disease, for other diseases also. If you see from this image, the good thing is you can play around the design. Whatever the design you want, you can just draw. It's like a drawing software. You just use the software to design whatever the design you want and just print with laser. After optimizing the laser, you will get the electrode. Once you get the electrode, you can play around. If you want to modify with nanomaterial, you can do receptor. Yes, you can do so. There are a lot of flexibility with that. And why laser-induced graphene electrode? So primarily, most of you are aware that graphene is like very popular. Everybody knows graphene is a fantastic material for last 15 years. In fact, I started my PhD with graphene. My first task during my PhD is like synthesizing graphene, and that time graphene was not that much popular. In fact, after I joined PhD, after 1 year, I think after that only Nobel Prize was given to graphene. So what I usually do synthesize graphene using wet chemistry approach, and it has so many steps. It starts from graphite. You have to oxidize with a very strong oxidizing agent like permanganate, sulfuric acid, H2O2, and so on. And then you have to do a lot of washings, filtration, centrifugation, and you will get a very sticky like graphite oxide. And then that graphite oxide has to be undergone ultrasonication or some other exfoliation method to get sheets of graphene oxide. Then you do reduction using, let's say, sodium borohydride or any other reduction methods. So this entire process is quite long, and you may end up with a aggregator graphene, right? So, and other method, CVD is a popular method to prepare graphene, but it's expensive. On the other hand, these laser-induced technology is straightforward, just a single step. All you need to have is a PA sheet and a laser irradiating machine. Just you optimize the laser, one step, and direct solid state. There is no solvent involved in the method. You will get a completely fully solid state graphene, and that's the biggest benefit of having LIG. Then I thought this is really great. After working with the solution state graphene for like 10 years, then I realized this is really nice, and I totally moved to making LIG graphene electrodes for last 4 or 5 years. And it gives completely 3D porous structure. Considering the focus of my talk, I didn't give the characterization information about this, but it's completely porous graphene, both microporous and mesoporous, meaning that we could do a lot of biofunctionalization. And it has like 70 to 90% carbon remaining. You have heteroatoms like nitrogen. And in case, since this conference is materials, I would give some materials introduction for that. So let's say if you want to make some kind of doped LIG, you could supply different kind of dopant during the lasing process. If you want more nitrogen, you supply more nitrogen gas. If you want some boron, then supply boron gas. You will get a heteroatoms. So this is like single step synthesis again, right? However, if you imagine how we make doped graphene in a traditional way, is you need to prepare graphene first, and then you put the graphene in a tubular furnace and supply the nitrogen or boron source or whatever source heteroatom you want, and then anneal them at 500, 600, or even 800 degree for few hours, and then followingly during washing steps. So again, we don't need such harsh steps to have doping using LIG method. It's just PA sheet, no baking step, no binder, no masks. And you could also prepare these LIG sheets using biodegradable substrates. For example, nowadays, people started to use like some leaves or even potatoes or some kind of crazy biomaterial as long as you understand the lasing process, doing multiple lasing, optimizing the laser parameters, you could get laser induced graphene, and that also lead us to have a sustainability. Right, and it's a completely disposable electrode, meaning that in medical diagnostics such as cardiovascular disease, we don't want to reuse the electrode, we want a disposable one, and you need a cheaper one. You cannot dispose something cost like £1,000. You need like at least 5 pounds or 10 pounds or 20 pounds to dispose that, and such a low cost electrodes these are, and they're flexible, meaning that we can use it for a wearable sensor, and they have a pretty good anti-fouling property, and that also can be tunable by controlling the environment you supply during the lasing process, whether you supply just air or you're supplying an inert gas. So based on that, you can play around and you could do roll-to-roll manufacturing. As I mentioned, it's just a complete manufacturing. So even every day I print here, every day at least I print like minimum 30, 50 or 100 electrodes we do printing. And it's a computer controlled, meaning that you will get an accurate geometry, whatever the shapes and size you want, you could do that. So what I wanted to convey you is making LIG graphene electrode, you have a lot of advantages. At the same time, you have a lot of controllability. You could control the laser powers. By controlling the laser parameters, you can control the property. Let's say you can control laser power, laser beam size, laser spot size, how small spot or how big small, how the speed, the scribing, and pulse per inch, how intensively you want to give. So all these parameters will help you to have a controllability, what type of material you want. Let's say some of the people, okay, I want to make a LIG for supercapacitor. You may need to consider different parameters. And some people use, I want to use it for fuel cell applications. You can think about different parameters. And I'm a biosensor person. I'm an electrochemical bioscientist, and I want a surface that has more porosity, more residual functional groups that help me to attach the biomarker. So I think about different way. Right, and in cardiovascular disease, another important parameter is we want a multiplexed sensors. What does that mean? A technology, or I should say electrode technology, that could give us an opportunity to detect multiple biomarkers simultaneously. As you know, cardiovascular disease is so complex, it releases a lot of biomarkers. It's always better to detect multiple markers simultaneously so that when you have more information, the doctors can make more stronger, more authentic, or more stronger judgment, I should say, more confident judgment. That's the word I'm looking, more confident in their judgment. As a result, medical intervention can happen so quickly and save the people, because remember, in cardiovascular disease, each minute is crucial. Even the technology save 1 minute, that's an advancement. So if you see on the left hand side of this slide, some of these multi-biomarker panel, let's say troponin T and HFA-BP, can help us to scrutinize acute MI. But let's say if you detect a CTNI and MPO, you can tell about ACS, acute coronary syndrome. So similarly, so different panels or different biomarker panel to give you different information about the cardiovascular disease. The idea is to get more accurate information about heart, which part of heart, which type of disease, so that doctor can make a quick decision. In fact, I have written a review article 2 years ago, very big review article that was published in 2022, and I talk about very detail of my experience on this field. And these excellent results that I and my team did a year ago with patient samples. So basically, we make a multiplex biosensor based on LIG electrode, and we tested in patient samples, patients who are affecting with AMI in Turkey, Ege University Hospital, and also we did some studies in KAUST, back in KAUST while I was there. and we also plan to do in other hospitals. And this technology is already in a very good TLR levels, and it's a research translation project. So what we did is we have a LIG electrode, and we originally wanted to use whole blood, but unfortunately we unable to get a whole blood diagnostic, so we have to use serum still. And after you get the serum, place it on the LIG electrode, and it's an aptamer technology that I will talk in detail in the further slides. So that's on the right hand side, you see 50 samples. So it's a quite long study, like 50 patients samples. We measured troponin I, troponin T, and CRP, and successfully our sensors are able to simultaneously detect these three biomarkers, and these results are very well in accordance with the standard gold standard ELISA method. Right, now let me move to materials part. So now I finished the electrode part, I'm moving to the materials part. So materials, and I think most of the audience are from physics department. You know the value of materials, you know the importance of materials. Materials have a significant role in all the research field, and that is also the case in healthcare technology. Materials, especially nanomaterials like 2D materials, are very widely used in healthcare technology, and they are really necessary for multiple purposes. And for my research, I use them for three purposes mostly. The first one is signal amplification, second one is surface area improvement, the third one is bioconjugation. In the signal amplification, what I mean, these material help us to boost the signal sensitivity. Let's say without material, you may just able to detect microgram per ml. With material, you can detect nanogram per ml. They help us to boost the signal sensitivity. And secondly, they help us to increase the surface area. Let's say LIG electrode, you have a certain amount of surface area, and you introduce additional material, the relevant right material, that also increase the surface area. As a result, you could increase signal, and also that surfaces can be used to tether or bridge the bioreceptors. And the third one is bioconjugation. That's the more important and challenging area, using these materials property to bridge the biomarkers and the bioreceptors on the electrode surface. So I use a wide range of materials, mostly graphene, maxenes, metal nanoparticles, metal oxides, and since it's applied research, I prefer simple synthesis. I don't want to do complex synthesis because that will bring more cost to the system. As I mentioned in the earlier objective is to have a low cost sensor. And if you see the bottom three small pictures, and I'm a lazy person to draw pictures, so I make a very simple pictures. So what I wanted to convey with these pictures is how to manipulate or how to tune the materials to help us connect the junctions between the biosensors. So in general, biosensor is nothing but generating information from your target analyte to the sensor. Let's say a cardiac biomarker, and there is some information in the blood, some health information, some information about heart is going on in the blood. What you want is you want a device that gather that information, because we human cannot understand that information. So we need a device that help us to translate that biological information into a readable digital information that we human can understand. So in that case, the information flow goes from target analyte, let's say troponin, to the receptors, and from the receptors to the mediator, and from the mediator to the interface to the material, and from the material to the electrode, and from electrode to the reader. So you see so many junctions are there, and when you have so many junctions, there are a huge chance you may get lost with the information. And there comes the role of 2D materials. So these materials help us to bridge the junctions and help us to have the all kind of information intact, so we get a best outcome from the sensor. So in my research, I do a lot of these tethering using materials to tether redox reporters, materials to tether receptors, materials to tether even targets sometimes. And this report was published maybe in 2021. And in this work, I show you how you can use nanomaterials attachment to increase the signal amplification. You see, I use laser-induced graphene electrode and then use the laser-induced graphene electrode to make a aptamer biosensor. I will talk about aptasensor later. So basically, then you deposit the nanomaterial on the working electrode, followingly attaching the DNA aptamer. It's a very typical procedure under MCH incubation for about 16 hours and followingly BSA blackage for 45 minutes. This is the way we attach the receptors on the electrode surface. You need to provide sufficient time so that they can assemble on the electrode surface and make a strong bond formation to the electrode surface. And then ferricyanide solution is widely known external redox mediator for a signal readout. Then you read the signal. The idea is when you don't have troponin I, the interface electron transport is faster and you will get a higher signal. When there is a troponin I in the blood present in the sample, because of these proteins, they block the electron transport, you will get a decreased signal. And you see the panel A of this figure, A to J, the first red curve is quite high. That's the zero CTNI, which means there is no CTNI. It shows very good signal, high signal. But once you started to increasing the troponin I concentration, the signal keep decreasing. And by the way, this is a DPV. And because of this decreasement, you will get a linear regression and you can make a plot. And from that, you can make a sensor out of it. Right? And it's quite selective and you can use it for sensing markers. And similarly, I, along with my team, developed a porous graphite carbon nitride gold nanoparticle for cardiac troponin I. The material synthesis is simple and straightforward. From melanin, we can prepare graphite carbon nitride and then make porous graphite nitride. And so this is a material synthesis is different. And then we make deposit that material on the LIG electrode. Then followingly, again, aptamer immobilization treatment. And it looks easy actually from the picture, but it's really challenging to optimize each stuff. We have to optimize the concentration of aptamer. You have to optimize the time for the incubation time for the aptamer. Sometimes you need overnight, sometimes you need less than overnight. And also the target unlight binding, we want minimum as much as possible. That's the most important thing, because once you have a sensor ready, you can make sensor even before in bulk synthesize, but we want the incubation time less than 15 minutes or even in minutes if possible. So that's the purpose. So you remember I mentioned in the ELISA the incubation time or the analysis time take like 4 hours. My job here is to minimize that to in minutes, and with this one we can do that in 30 minutes. That's a very good improvement. All right, this is another sensor for electrochemical transistor. This is a little bit different than electrochemical voltammetries, where we measure the output current and we apply here the little bit source drain current stories that I'm not going into detail. But what I wanted to say is with these LIG electrodes, you could make different kind of electrode systems. Right, I think I'm almost 9:17. I would prefer to take 7 or 8 more minutes. Let me move on to the second part. That's about bioreceptors and biofunctionalization. That's the most important part. So in terms of receptors development, if you see on the left-hand side of this presentation slide, there is a material and the lines represents the bridging, and then you have these yellow red color DNAs, proteins, all those stuffs. So this is something really important picture. What I want to say from here again, this biological world, right? You have DNA, proteins, peptides, these and all biological world. Their language of communication is different. Their world is entirely different. And you see the material on the bottom, and the material behaves differently. These are two different worlds, and we have to find a right strategy to attach them. Mostly I use EDC NHS coupling to have a carboxyl NH2 coupling or gold thiol coupling when we use aptamers gold thiol linkage. So either covalent linkage or electrostatic interactions or pi stacking interactions, since these 2D materials have a lot of pi bonds. So if we make use of that pi stacking electrons, we could also make materials and biosensors out of that. On the right hand side, this was done by a professor in Kaust. What they did is they use pi stacking interaction to make a single step functionalization. This is really good because they minimize the number of steps involved in the functionalization. And aptamers are very widely used, and I myself like aptamer very well because aptamers are quite stable, thermally stable compared to antibodies. So there's aptamer of like 50 mers. So mers is nothing but how many number of DNA DNA monomers like you can have. So 50 to 70 mers generally you can have for aptamers. And it's an antibody sensor for CRP done by my colleague. Right. So that's about bioreceptors and biofunctionalization. That's a very big area. And considering the audience, I limit that chapter. But you just remember that we need to have a right technology to have a bioreceptors and sensors. And the final one is diagnostics and integration. That's about electronics, the readouts, cyclic voltammetry, DPV, and such stuffs, and also integration stuffs. And I mostly use electrochemical readouts, but I'm interested in making integrated point of care devices. That means integrating all the things together, make it as a package so that doctors can quickly use it at the hospital. And also I thinking to work with a wearable heart monitoring and implantable sensors. Those are really helpful for continuous monitoring applications. And this is one of the miniaturized potential state I and my team made in 2022. You see this coin, just a coin shape, like very small, and it weighs really, really small. And with this device, you can make a sensor out of that, and you just place the electrode, insert the electrode to the adapter, you place the sample, and you get the reading. And this device is really, it's a in a TRL higher level. We have a patent for these technologies, the electrodes, miniaturized potential state, smartphone. You see, you can combine everything together and you can use it. Any person can use it basically, and it's handheld. And with that one, we made a multiplexed biosensor in the lab. And also we are thinking to develop signal translation, mimicking the BMI meter so that even non-technical people can understand what we are talking. So the idea is making the technology more user-friendly, whatever means. It could be the way how they use, it could be the way they do sampling, it could be the way you can understand the signaling. So all the things we think about user-friendliness. This device is made by the our spin-off company in the center, and this is, you see, quite small, very, very small and highly robust. It's a fantastic technology. It's a just recent spin-off companies. Millions of dollars are going on, and hopefully we will get a good device in future. And here I show you some of the examples for commercially available cardiac biosensor. These are very recently invented. And the most important to me is iStat from A-Boot point of care. That's, but the thing is, they're sensitive, but it's expensive because it's based on enzyme antibody. It has a huge production cost, and my idea is to make it as cheap as possible. These are some of the future directions: point of care sensing, implantable devices, and so on. All right, let me recap all the story, whatever I talked to you. Maybe it's too much for you. Let me give you a recap. So what are the points I want to take home message for you? Cardiovascular disease are the bigger killer in the world, and it is really, really complex disease. We just call them heart attack, but that's a very blended term, but it's really more complex. There is a lot of different types of cardiovascular disease. It's really important to do early diagnostics. That's the first step to stop this epidemic. and it really requires user-friendly and handheld diagnostic device. The way currently we do diagnostics is so complex, expensive. We have to use a lot of imaging techniques, x-rays, CT scan, followingly blood tests, ELISA. What we need is we need a low-cost, simple, user-friendly diagnostic devices that quickly measure the blood biomarkers and tell the user whether that person has something wrong with the heart or not, so that that person can go to the hospital now and do the expensive stuff. So we wanted to make such devices. That's the idea of this entire talk, and that was the research I'm doing for last 5 years and maybe next 5 years or 10 years, because of a lot of things to do in this field. And I work with electrochemical technologies. I mentioned you why I'm interested in electrochemical technologies, why I believe they're fit for that. Just 3 points you remember: they're low cost, they're user friendly, they're completely portable, handheld. The best way to remember is a glucometer, such a simple sensor. So we wanted to make such a simple user friendly diagnostic devices. And I structured my talk into the 3 categories: electrodes and materials, where we require development. The second area where it requires development is bioreceptors and biofunctionalization. And the third area where we want need development is diagnostics and integration. And then I jump in to talk about electrodes. I hope you get some idea about LIGs, laser induced graphene electrode. These are solid state electrode, single step direct graphene synthesis, way better than solution process graphene. And you can play a lot around just tuning the drawing. You can make multiplexed electrode, you can introduce microfluidics, you can introduce filters, and so on. And materials, broadly, I work with the 2D materials like graphene, maxines. You can use them for multiple purpose: to increase surface area, to have a signal amplification. And the idea is help use them to connect the biological world with the electronic world. And I also talk about bioreceptors. I didn't go detail considering the time, but generally antibodies, aptamers, DNAs, these are the most widely used bioreceptors, and I mostly use aptamers. And followingly, bioconjugation. Again, the bioconjugation is a very big topic. It could just, you remember, bioconjugation is having strategies or crosslinkers are bridge to connect the receptors to the electrode surface through these forces. And I then talk about diagnostics and integration. I didn't talk much about that considering the time, but it's all about integrating different stuffs, integrating electrodes, integrating a device, integrating IoT, integrating even AI stuff that we are doing here. So integrating everything together, get the maximum out of these testings. And we could also make continuous monitoring for post-heart attack monitoring. That's really a very important field, because once a person get a heart attack, there are more chances he or she will get a heart attack in subsequent days. So it's better to have a post-heart attack. And I talk about commercial market. There is a huge market for these technologies, especially the current devices are expensive, and we need a less expensive one. And also current technologies are not user friendly, not all of them user friendly, so it's always room for development. All right, thank you so much for your attention, and I'd be happy to take some questions. Hello sir, can you hear me? I think you're muted, so you have to unmute yourself. Sorry.
And due to lack of time.
Yes. Right. Now I can hear you. Before I can't hear you. Right.
Yeah. So my students can contact you directly by email for any clarification, sir.
Yeah, definitely. I'm always happy to receive emails. If you have any questions, you could email me. Yeah.
Oh, okay. Thank you so much. Thank you so much. Over to Dr. Kanik Raj.
கேக்குதா? Sir, can you hear me?
Yes, I can hear you well.
Sir, I have one question. Why we are unable to fabricate reusable sensor for especially glucose measurement? Because every time we need to use a separate sensor, no, which costs more.
I mean, you are talking about electrode,
Yeah.
right?
No,
Electrode,
sensor.
right? Yeah, electrodes, because sensor is a very big term. So we talk about electrode. You can use the reader for multiple times, but the electrode, you can, theoretically, it's possible to reuse them. We will do reproducible tests. But the medical field or healthcare field is really very, how to say, we don't want to have we want something disposable, just one time use, right? So that's something we really want that.
No, no, no. The principle behind this is only this resistive measurement, no? Only the resistance change is measured that
Yeah.
reveals the
So
glucose level.
not only, let's put the example glucose, right? We are using a drop of blood and there are a lot of proteins there. And once you use the sample, there are chances the proteins stick to the electrode surface. Once something stick to the electrode surface, it compromises the quality
Yeah,
of
is
the
it
electrode.
not possible to clean everything?
It is possible. For example, in fact, we are making anti-fouling coatings. Nowadays, you have a continuous glucose monitoring that's called CGM that do multiple tests. So in future, not in future, even currently, that device is called artificial pancreas. So that do continuous monitoring and not only repeatable like 1, 2, 3 measurements. It can work for a week. So we are talking about more than a week nowadays. So that's what you are measuring there. We do a lot of repeatable measurements because the surface is passivated by fantastic films, anti-fouling films. So they're kind of acting as a god to filter these proteins from the blood. Yeah, it is. It's really possible.
Okay, thank you. So on behalf of all of us gathered here, both present here and online participants, I thank Dr. Veerappan Mani for his highly technical discussion or lecture here. So thank you, sir.
Thank you so much, and
Thank
thanks
you.
for the
Thank you.
invitation. Yeah.
Students, if you have any doubt, you can contact as our HOD told us through email. Email is with our HOD. You can get it and you can contact him. Thank you.
Thank you, sir, for sharing new sites about cardiovascular disease and the diagnostic device. Also, we are truly inspired by your vision to improve heart health to all. I also extend my gratitude to Dr. B. Kanikraj for chairing this session. Thank you, sir.
Precision and accuracy are the hallmarks of progress in science. Now I welcome Professor S. Dominic, Assistant Professor of Physics, St. Joseph College, to chair the...
Let me leave the room. Is that fine? Right.
Yes, sir. Thank you, sir.
Okay. Thank you so much. Best wishes for the success of this entire conference. See you. Bye.
Sir, good evening, sir. Dr. Vijayan, sir, good evening.
Sir, can you hear me? You are unmuted now.
Yeah, I am audible to you?
Yes, sir, you are audible. Could you please turn on your video? Sir, can you hear me?
Yeah, but my video is, I hope you have to give me a permission first.
Just check. Yes, sir, your slide is visible now.
It is in the full screen mode.
Yes, sir.
It is changing.
Yes, sir.
Yeah, fine, I am ready.
Just a minute, sir.
Yeah, I am ready. Maybe, yeah. So whenever you are telling that. Johnson sir, I am audible?
Yes, sir, you are audible, sir.
Yeah.
Yes, Dr. Vijayan, you please start. I request Dr. Dominic to charge a session.
Okay, no problem. Otherwise, I mean, I thought that maybe you are planning something. So
No.
now?
Yeah, it's very well. We wanted to have it in the two screens. One screen is visible. That's we will make it. Okay. Dominic, start.
Good evening to all. I am honored to introduce our resource person, Dr. N. Vijayan, the Senior Principal Scientist, CSIR NPL, for this momentous event, ICAM 2025. He finished his BSc MSc Physics in our college. It's an alumnus of our college. We're really proud of the illustrious alumnus of our college. He finished his BSc MSc in our college and MPhil in Bharatidasan University and PhD in Material Science at Anna University, Chennai. He occupied various positions in CSIR, such as joined as a junior scientist and then moved to scientist, then senior scientist, then a principal scientist, and a senior principal scientist in CSIR NPL, National Physical Laboratory, New Delhi. His research interest is growth of single crystals by melt and solution growth techniques, preparation of Indian reference materials for the calibration of sophisticated instruments, and preparation of nano and allied materials. He has published more than 240 papers in the reputed international journals, and he has authored 5 books. He also developed patent materials. He received several awards in the field of research, such as a Best Paper Award, Bharat Excellence Award 2014, Best Innovative Research Award in 2015, Outstanding Researcher Award in 2017, and Dr. S. Gunasegaran Award in 2018, then Raman Research Fellowship in 2021, and Young Achiever Award in the year 2022, and so on, because he received more than 17 awards. His research activities goes more than 5 pages. To save time, I leave it to all to refer using website. Such an eminent person is with us today to deliver a speech on advancing instruments, calibration, India's path to Viksit Bharat through indigenous standards. Now, I would like to welcome Dr. N. Vijayan, the Senior Principal Scientist, to share his experience and to motivate the future scientists in the field of advanced materials for advancing instruments calibration. We welcome you, sir.
Thank you.
Now we can start our presentation so that our students eagerly waiting to hear a lovely speech. Thank you, sir.
Thank you, Chairman, for your nice introduction. Yeah, I am audible to you. I am audible to all the participants.
Yes, sir.
Yeah, my slides are changing. Can you confirm?
Yes, sir. Yes, sir. Please proceed, sir.
Yeah. So anyway, before going to my presentation, first of all, I would like to thank my temple. I am proudly say that I am alumnus of St. Joseph's College, and I am thankful to my guru, Professor Johnson, sir, and then other dear faculty members of this great institution. Whenever I used to cross Tiruchirappalli, I used to wish my great institution because I learned many things through that institution. So thank you, sir, for giving the very good chance. So my dear participants, anyway, today and then tomorrow you are going to hear many lectures. Various research fields are there. Now I hope in the offline participation, many students from various research groups and many students, maybe they are doing post-graduation. Maybe few of the students, maybe they are doing for undergraduation. I hope my talk, it is not based on the research. It is like a awareness talk. What is the current scenarios in India in the area of science and technology? So that's what I have chosen this title. Advancing in the measurements, that is calibration, India's path to Viksit Bharat through indigenous standards. Here, I wish to recall that, India, we got the independence in 1947. But till date, we are using our chappal size. It was designed or it was determined by somebody else. We got the independence in 1947, but we are not having our own BP values of our own Indian citizens. We are following some other countries' blood pressure. If it is higher, then immediately we started taking the tablets. Regarding the sugar level also, CSIR taken initiation that why not? Almost we are going to pass within 22 years, 100 years of our independence. But till date, each and every technology, we are depending the other nations. Enna valam illa inda Tirunattil. We are having everything. Nature has given everything for our needs. And India is such a place that we are having different varieties of culture, different languages, and at the same time, different climatic conditions. If you take from Kashmir to Kanyakumari, Kashmir, you can compare the temperature, and middle of India, you can compare the temperature and then humidity, and southern part of India, you can compare the humidity and then temperature. And you can see the height of the persons. Height is also varying from one place to one place. But how we are deciding that we are following somebody has determined the size of our chapels and we are following from the past many years. And somebody has determined the blood pressure value and till date we are following. And CSIR, they have taken initiation that soon, I hope, they are going to declare or they are going to finalize the size of our Indians' footwear, the values of blood pressures of our Indian continent, Indian conditions. These are all the few examples I have given for the youngsters. So, I am wishing that the conference organizers, they have taken very good initiation, and I hope today and then tomorrow you are going to enjoy various lectures. So come with me and then join with me. We will walk through towards Vikshit Bharat. At least before 2047, we will become self-reliance. Not necessary to depend the other nations. India is the excellent place. We are having more than 150 crores of Indians. You can take the other countries. They are not having this much human resources because human resources are very, very important for the development of any nation. Less than 40 years of age, more than 50 crores in India. Population 160 crores. But what are all the gadgets we are using? Whatever you are using, cell phone or computer or maybe your refrigerator or air conditioner, all are made in some other country. Why not? We can able to make our own. The countries, they are not having the population. They are making the products, but they are using India as the platform for selling those products. They are earning crores of rupees. The simplest example, today is 30th January 2025. Exactly after 28 or 27 days, we are going to celebrate the National Science Day. I used to say in all platforms, maybe some of the students might be attending my sessions, maybe in various places. I used to say because this is the awareness. We have to disseminate the informations to all the scientific platforms. Raman is an Indian because St. Joseph's College is also in Tiruchirappalli and Raman belongs to close to Tiruchirappalli, that is Srirangam. He discovered the Raman effect in India in 1928. 1930, he got the Nobel Prize. 2030 is going to come. But if you see from the past few decades, even from the past 5 to 6 decades, no Nobel Prize from India. That is another part. And if you see that Raman has designed the equipment very less cost, less than 500 rupees. And we are all very proud. He is an Indian. He designed the equipment in India. But the condition is Raman spectrometer we are purchasing from Germany. Raman spectrometer we are purchasing from the other developed nations. Why I have insisted the developed nations? The countries, they got the independence almost 1940s or 1950s. And we are calling those countries, many of the countries, developed nations. But whenever we are talking about our own nation, our mother nation, we are always calling us developing nation. Why not we have started calling India as the developed nation when we are going to call India as the developed nation? It is not a big secret. Everywhere human resources are same. Everyone is gaining the knowledge. And what is the drawback? Everywhere human resources are same. And we are also gaining the knowledge. The developed nations, they are also gaining the knowledge. And where is the drawback? But what are all the knowledge they are gaining? They are converting those knowledge into products. They are converting those knowledge into devices. They are converting those knowledge into technologies. But in our nation, what are all the knowledge we are gaining mainly through the academic system? Our knowledge we are compiling at the end of the MSc or at the end of MTech or at the end of PhD. we are compiling in a thesis form comprising of, if PhD thesis is approximately 300 pages, if MSc thesis is approximately 50 to 70 pages, we are compiling after BIOS examination, we are displaying that thesis in departmental library or college library. See, now you can say our knowledge is not going beyond our library. Our knowledge we are not transforming into products. Our knowledge we are not transforming into devices. So that's what I have given title. At least within another 22 years remaining, that means approximately we are having another 2 decades. At least youngsters, what all the research work you are carrying out. I am not saying that you have to do particularly in one field. You can do n number of fields. But always remember what are all the research outcomes you are getting. At least you can correlate into some product, some useful societal devices, some useful technologies, because Indian total population is 160 crores. Each and every one, it is very difficult to expect government to give suitable jobs. Instead of that, by using our own technology, why not we can become entrepreneurs? By using our own technologies, why not we can become startup partners? By using our own technologies, why not we can sell our devices to the other nations? Our Honorable Prime Minister Narendra Modi ji used to mention that now we are simply importers. Whenever we are transforming from importing level to exporting level, then definitely India soon will become developed nation. So this is my main theme of my presentation. So let us travel. Welcome to National Physical Laboratory. National Physical Laboratory, it is coming under Council of Scientific and Industrial Research. For the MSc students, I hope everyone knows about the CSIR. CSIR is also conducting Junior Research Fellowship for your higher studies. CSIR is also sponsoring projects for various colleges. CSIR is also giving Senior Research Fellowship as well as conference funding for all academic institutions throughout India. In addition to that, CSIR is having 38 laboratories across India. You are in Tiruchirappalli. Close to Tiruchirappalli, you are having Karaikudi. Karaikudi, we are having our sister institute that is called SECRI, Central Electrochemical Research Institute. In Chennai, we are having another CSIR laboratory. That theme is totally different. That is called Central Leather Research Institute. CSIR was formed almost a few decades before. Some of the laboratories after independence, some of the laboratories before independence. National Physical Laboratory, the first foundation stone was laid before our independence. That is 4th January 1947. That time the interim government headed by the then late Prime Minister of India, Pandit Jawaharlal Nehru. And very interesting information. The first founding director of National Physical Laboratory was the student of Sir C.V. Raman, and his name is Dr. K.S. Krishnan. The first founding director. You know where he belongs? He belongs to a small village. Now also in that village, only few buses are going. You can imagine before our independence, how he traveled to capital and he became the first founding director of National Physical Laboratory. See, many lessons we have to learn from our premiers. Many lessons we have to learn from our forefathers. That was the dedication. That was the hard work. The village name is Battira Irpu. That is close to Srivilliputtur. He was the first founding director of National Physical Laboratory. And I am requesting all the participants, in case, I hope I am seeing some of the participants online, some of the participants you are attending offline also. In case if you are having any chance in the future, you can visit National Physical Laboratory. And in addition to that, you can also see very beautiful historical places in New Delhi. It is not necessary to visit the other countries. In our own nation, we are having beautiful places everywhere. Sometimes, maybe during your summer vacation or maybe summer internship, even Government of India, they are giving your summer internship also, free of cost, with the stipend, with the free travel support. But how many people we are utilizing? Government of India, they are giving scholarships. But how many people we are utilizing? Government of India, they are giving junior research fellowship, senior research fellowship for doing higher studies. Not necessary to depend your parents. You can stand by your own leg. But how many we are availing? So these things we have to keep in mind. So National Physical Laboratory, it is located almost in the central part of India. It is a beautiful place. Whenever you are visiting in the future, you can come and then see the National Physical Laboratory, not for seeing purpose. You can see what is the real research is going on. Whether National Physical Laboratory, they are working for the development of various societal based products, or they are really working for the development of various devices or various technologies. So that is also there. You can come and then you can see the beautiful campus of National Physical Laboratory. And I hope many of the students, you started reading in the newspaper from the past few days, One Nation, One Time. I hope some of your faculty members like Dr. Anbarasu, Dr. Alexander, they have already visited this place, this beautiful place. And even some of, my own guru, Johnson sir, he used to visit regularly. And other faculty members also they have visited, Dominic and then other members. I hope a few days before, you started reading from the newspaper that One Nation, One Time. That One Nation, One Time is based on the Indian Standard Time. That is called IST. IST is maintained by National Physical Laboratory. So National Physical Laboratory, we are having different names. One is National Measurement Institute of India. Another one is National Meteorological Institute of India. And other name, colloquially we can call as the timekeeper of the nation. Why this time is very important? Nowadays, you are seeing a lot of cyber frauds, right? You are using your digital transactions. Where you are using your digital transaction, at what time, what second, that is again based on the IST. Our ISRO, we are having MOU. Our Indian Air Force, we are having MOU. And Indian civil aviation sectors, we are having MOU based on the Indian Standard Time. So that much, lot of informations are there. It is very difficult for me to explain each and everything. I am requesting the students, you can go and then see. Nowadays, you are having all the world in your hand. You can just put about the National Physical Laboratory, what all the research work is going on in National Physical Laboratory. You can go and then you can see. But you can see in the corner, I have mentioned the SI units. Top, I have mentioned the CSIR NPL. What is the relation between SI unit and then CSIR National Physical Laboratory? In my earlier slide, I have mentioned that National Physical Laboratory is the National Measurement Institute of India. So what is the relation between national measurement and then SI unit? Now you can recall during your +2 or maybe 10th or maybe your school days or maybe your graduation, you studied about the 7 basic SI units, right? Distance, immediately you can say meter, time, second. So like that, 7 basic SI units are there. But normally we used to read for our exam purpose. After that, sometimes we used to recall, sometimes we are not thinking about that. Now you can recall all 7 basic SI units. All the 7 basic SI units are very important for smooth life cycle of each and every citizen of in our nation or all over the country. Each and every action is based on the 7 basic SI units. If it is not properly maintained, it is very difficult to imagine a single second in our life. So all the basic 7 basic SI units are maintained by National Physical Laboratory. So these are all some of the historical pictures or recent events. NPL normally used to open almost end of September every year. That is called the Open Day celebrations, because Government of India, they are supporting the general citizens, taxpayers' money. Everything, it should be accountable. So anybody can come and then they can see what real research NPL is doing. So college students, school students, even the general citizen, they can come and then they can visit National Physical Laboratory. And you are seeing Dr. K.S. Krishnan is interacting with the then late Prime Minister of India, Pandit Jawaharlal Nehru, during the inauguration of National Physical Laboratory. What Nehru was mentioning, instead of becoming Prime Minister of our nation, in case if I will get the chance to become the Director of National Physical Laboratory, I am the happiest person. So that much credential NPL is having. So whenever your time permits, you can come and then you can see National Physical Laboratory. Now, we will see what are all the general science and technology trends in India. See, we got the independence in 1947. Now almost 76, 77 years are over, 78 years are going to be over. But even we are depending for small hooks and then pins from other nations. So then other things you can add. Cell phone, it is very difficult. Or maybe automobiles. Indian roads are filled with other countries' automobiles. Even our own home, sophisticated gadgets, refrigerator, air conditioner, or what are all you are using for based on artificial intelligence, all are at least made from other nations or the technology from other nations. So I am asking you, yes, definitely we have to make our own products. 77 years we are doing our research and basic research and technology, or basic research and then development. But when we are going to make our own small devices from our own research, even if you go and then see outside of our campus, outside of our house, it is filled with plastic. Nowadays, you started reading in the newspaper that already our blood vessel, microplastics has already entered. And it has gone to up to brain level. And in the next few decades, it is going to change our DNA system. Whether we are having any proper solution for this? Seawater contains the microplastics. And one thing we have to make a note, that anyway, why I have to bother? My house is neat, my campus is neat, I am coming and then going back. Why I have to worry? But remember, what are all the table salt you are taking? It contains the microplastics. What are all the water you are taking? Drinking water, it is having the microplastics. Even the metropolitan cities, highly densely populated areas, even the air particles are having the microplastics. Now you can imagine, without solving this, how we can able to go for very advanced research. In India, we are having more than 35 to 40 crores below poverty line. They can't able to afford for 1 liter of purified water. Approximately outside you are getting 30 to 40 rupees, right? Even 1 liter of petrol you can able to purchase within 100 rupees. 1 liter of water is almost equivalent to the cost of 30% of or 40% of the cost of 1 liter petrol. But that is really worth to purchase 20, 30, 40 rupees per liter of water. But have we thought of the below poverty line? Whether they can able to afford for at least 4 members in a family, at least they need 20 liters or even 10 liters of water for drinking. 10 int multiply by 20 or 30, 300, 200 rupees. How it is possible? Whether we can do the research, we can find out the technologies. affordable water purification system. From the dye water into a potable water, and the conversion cost is less than 30 paise, 30 rupees into 30 paise. That is called the real societal research. See, I used to show this because we have to make awareness throughout our research communities. Birds started eating the plastic. Cattle started eating the plastic. Deep sea animals started eating the plastic. Then whenever I used to discuss this, immediately some students, they used to ask, why government is not taking steps? Because we can able to control through by putting stringent rules and regulations. But we should not, I am saying you, we should not blame the government. I am asking you, who invented this plastic? Researchers community like us, we only invented the plastic. Whether we have given the solution for plastic recycling, now we are doing some other research and we are talking about the plastic recycling. But now situation is beyond control. Every day, thousands of tons piling up in the sea or in the plain areas or in the air medium, water medium, everywhere. But whether we can do the research, whether we can combinedly work to find out the new technologies for this. So join your hands with young researchers and you can make your own small startup industries. You can make your own app. Nowadays, anyway, now at least awareness is there. Earlier days, even car booking app or what are all the things, some foreigners they developed and then they are earning crores of rupees. Even you can make the app, you can combine the scrap dealers under one roof and you can make it wonders. This is the example. Plastic normally they will not collect, but they will collect the electronic e-waste. Electronic e-waste can become the next problematic issue in the future. But whether we are having the solution for that, or can we make all the scrap dealers under one roof? Can we collect all electronic waste? I should not say waste. It is wealth. Whenever you are doing recycling, you can make some product. Whenever you are doing recycling for the electronic materials, you can get precious metals. So how we can call as the waste? But we have to find out the solutions. We have to find out the technology for making waste into wealth. Now you can say, can you able to say that this is the government fault? I can able to say that this is not the government fault. Politicians, they have not invented the plastic. Researchers like us, we only invented the plastic. Nature has given everything free of cost. Water, even you can ask your parents, nearly at least 3 to 4 decades before, whoever comes or whoever visits our house, immediately we used to offer coffee, tea along with water, right? You can ask your parents, those days, they never ever purchased the water from the shop. No. Within 3 decades, how much pollutions we made it. We tortured our planet. Homo sapiens like us, we have not properly we have not given proper respect to our Mother Earth. We started purchasing the water, but water was given by nature free of cost. Even foreign companies, they are earning crores of rupees. Not only that, now I am telling what are all the breathing you are doing every day, every second, every minute, how many breathing you are doing. Now you can able to enjoy, but now it is free of cost. But after few decades, your generation, your own generation or your next generation, they have to pay for breathing the oxygen. That time, they used to mention that once upon a time, air was totally free. But now we started purchasing air from the maybe some other foreign companies. What about the solution for this? So these are all the things I have given the simplest ideas. But this is not the only problems. You can go and then stand in front of your street. You can go and then stand in front of your institute. What the general citizens are facing. Whether we can able to give any small solution for that. See, why we need a solution for this? I am giving simplest example. Why we need a good roads? If the roads are getting damaged, if the vehicle is going, if the distance is one place to another place, 10 kilometers, if the road is good, you can able to reach maybe within 15 minutes by consuming, because you are going normal speed and by consuming less amount of petrol. But the same case, if the roads are totally damaged, the same 10-kilometer distance, earlier you traveled within 15 minutes because of the bad roads. Now we are taking another 15 minutes more, that means 30 minutes. Now you can imagine your engine is continuously on for another 15 minutes. How much petrol consumption? Whether we can able to use our plastic waste for making the roads. Yes, roads will get damaged because no heavy vehicles are, because India, here again we are calling as the developing nation. Heavy vehicles are moving, industries are there, lot of population, everyone is having their own vehicles. Yes, but we have to give the solution to the government. By using the plastic waste, can we make our own plastic roads? By mixing with the tar and then other materials. So these are all the small examples. Now you can imagine, instead of 15 minutes, it was utilized almost less than 1 liter of petrol. But now the same distance we are using approximately 2 liters of petrol. Now you can imagine, one vehicle is using 1 liter. Crores of vehicles are using that road, that means crores of liters. Crores of liters we are taking these petroleum products from the other nations. That much foreign currency we are spending. Now you can convert crores of liters of petrol we can able to replace. For that we need a technology. This is the simplest understanding purpose only I have given the examples. Anyway, I have taken the example of vehicle. Now all government we are encouraging for the e-vehicles. Why we have to use the fossil fuels? But e-vehicles based on batteries. Anyway, a lot of new technologies are coming, lithium-ion battery or sodium batteries. Many technologies are coming. But again, like here, you are seeing a lot of electronic boards. In the future, everywhere you can able to see a lot of batteries. Each and every battery, the whole lifespan is 3 to 5 years or 6 years. After that, anyway, you have to replace. Instead of replacing, instead of making our own nation like a dump yard, can we find out some new nanomaterials or any materials? Can we inject one small amount into the already existing battery, and that battery lifespan is increased another 10 years? Can we do the research? Can we be able to think in this direction? One nation, one time. That is very good. Anyway, now the draft version is there. You can go and then see. Another one, why not? India, we are having more than 100 types of cell phone products. 100 types of cell phone products, 100 types of chargers. Why not one nation, one cell phone charger? If you are throwing your cell phone after expiry, you are throwing that charger also, because that charger will not suit for others. Why? We can insist the companies to make a one nation, one charger. So these are all the small things for developing the new ideas. Anyway, I will come because I am having less time. National Measurement Institute of India, I have already explained. NPL's contribution to our nation, enormous. even almost 10 months before or 9 months before you voted, right? The indelible ink during voting, it was the product from the National Physical Laboratory. And a few weeks before we celebrated the Indian Constitution Day, Constitution was written by the great Ambedkar, and it is still maintained by National Physical Laboratory in our Indian Parliament Library building. So like that, n number of technologies, n number of products given by National Physical Laboratory. Anyway, National Physical Laboratory, I am giving simple understanding purpose only. Now you are in Trichurapalli, right? You can go and then measure your blood pressure in 2-3 places. You can go and then measure your blood sugar level in 2-3 places. Maybe Karamandavam or Tepakulam area, or 2-3 places. You can compare the data. You are getting the same result. If you go and then measure your blood sugar level similarly, whether you are getting the same data. If you show this one to your doctor, even the person is not having the BP because of the wrong instrument data, doctor, he will not verify the instrument. Finally, he suggests to take some medicines. If the person is not having the BP or sugar, he started taking the medicines because the instruments are not properly calibrated. Now I will come to my point. This is the simplest example I have given. What about our sophisticated instruments? We are using X-ray diffraction. We are using scanning electron microscope. We are using TEM. We are using more advanced VSM, and many things are there. FTIR, UV visible. These are all the basic instruments. You can send your material 2-3 places. You can compare the data of XRD whether you are getting the same. I am not saying everywhere, but many of the places. So, instrument is not wrong. Instrument is working, but time to time, we have to calibrate that machine by using the indigenous standards. You can see our National Physical Laboratory, we are having 6 divisions. Our division, that is called the Bharatiya Nirdeshak Dravya. In English, it is called the Indian Reference Materials. So we are making our own indigenous standards for calibration of your FTIR, calibration of your XRD, calibration of your UV visible. Maybe you are having some doubts whether NPL is the first one for developing this. No. It is there already. All countries they are making. But till now we used to purchase from the other nations by spending few lakhs. That's what I used to say. Raman designed the equipment less than 500 rupees cost. But Raman spectrometer we are purchasing from other nations by spending few tens of lakhs. Similarly, indigenous standards, you can able to purchase maybe approximately 1 lakh to 1.5 lakhs or 2 lakhs. But the same material you can able to purchase by spending few lakhs of rupees. So we can able to call this material as proudly made in India. This material as the import substitution. So that's what we are going to see maybe within few minutes only, because I know that I should not take more time because many of the participants are waiting. So this is coming under metrology. That's what I have given earlier. National Physical Laboratory is also called National Measurement Institute. National Physical Laboratory is also called National Metrology Institute. What is metrology? I hope you know that meteorology, IMD, right? Indian Meteorological Department. They used to give warning or advanced predictions about the weather reports, right? That is called meteorology. But whatever you are going to learn today, that is called the metrology. Metrology is the science of measurement. What is the science of measurement? Even you can take 2-3 scales. You can compare the centimeter level, whether all centimeters are exactly matching. Not. And now we are doing nanomaterials, how we are ensuring that nano level size is perfect. That's what metrology comes into the picture. We have to do science in a scientific manner. Whenever you are doing perfectly, your technology is perfect. What are all the devices you are making through that, everything will work perfectly. So the base is metrology. The base is science of measurement. So I like this slide because I'm a crystal grower. I like great Sir C.V. Raman sir. And you know, we are all very proud. He won the Nobel Prize in 1930. But one thing we have to make a note, we are in 2025. After 5 years, we are going to celebrate the 100th year. But at least we can start traveling towards for getting the Nobel Prize in the future. Even the small nations, the total population is less than 10 crores. Each and every year, I hope recently you have seen the Nobel Prize winners. Why our name is not coming? So we have to rigorously try. Instead of wasting our time in the social platform, at least we can try to make wherever, whatever the field you are working. So we need a dedication. Definitely, I hope you will do it. So anyway, I will skip some of the slides. So everything, metrology is based on 7 base SI units. That is called the different SI units. So whenever you are doing metrology, you can do science in a perfect manner. So whenever you are having proper measurement, whenever you are purchasing any product, you are happy. And whenever the manufacturer, they are manufacturing and he is also selling without getting back the product because it is perfect, he will also be happy. So the 2 ways, so that is the measurement plays an important role. So whether we are having this many reference standards, I have given simplest example of sophisticated instruments, we need a reference standard. What about the cement? We are using different grades of cements for our house construction or industry construction. It is going to maybe another 30-40 years. But whether these cements are properly made it, whether we are having proper standards, what about the drugs, Ayurvedic products, each and everything we need a standard. So we are joining our hands with the private reference material producers across India, almost 11 MOUs with the private sectors. We are encouraging them. They are also started making reference material that is called the indigenous standards. So many things, whenever we are having our own standard, now you can correlate. I am having my own standard. Why I have to purchase from other nations? Slowly, it will impact in our economy. If lot of industries, if it is coming forward, each and everyone they are making, starting up small industries, then how many people they will get the job? So definitely one day it will impact in our economy also. So many things, I will not take your time. So this is my main concept. I have given few examples also you can go to. Nowadays, we are talking about the advanced materials. We are talking about the new inventions, new technology. All are based on some conclusion. How the conclusion is coming? Based on some characterization or examining the materials. How you are examining the materials? Even our pharmaceutical sectors, many sectors, automobile or maybe civil aviation, many sectors, you are using some instruments. So that equipment should be in a proper form. It has to give you a proper result. If it is not proper, wastage of money. How many hours you worked for that material, it will go waste. And finally, what are all the reports you are reporting to the scientific community? Always remember, it will not reflect in your name. It will reflect in our country's name. Scientific image of our nation. So many things are there. So I have given simplest example, XRD. XRD everyone knows. We are using for phase, shape, through Schiller formula, structural, you are determining crystal system, many things. This is the simplest equipment, Bragg-Brentano geometry. These many samples you are using for examination. In case your 2 theta changes, what will happen? The peak has to originally appear at 20. If it is shifting to 21, then you will say that my material is newly synthesized. And you are calculating your Schrer formula by trusting that full width of maximum is perfectly all right. If it is wrong, then your calculation is wrong. You are thinking that you are adding some dopants and that XRD machine is not having proper intensity. Your dopant peaks may not be visible. So this is the simplest understanding purpose only I have taken, because theta is very important, because 2D sin theta, everyone knows about the Bragg's law. Whenever I am talking about the Bragg's law, I have to mention here, recently I visited American College. I know the great professor. So he requested me to visit one of his laboratory building. There I have seen Bragg's in 1950s or 1960s. He came to American College. He has given a wonderful lecture. That's what, after seeing this Bragg's, I thought of mentioning this information. See, if 2 theta changes, or your intensity changes, or your full width of maximum if it is not proper, so everything it is having. So, how many XRD machines? It is not only one. This is the simplest survey I have done. How many industries? How many colleges? How many research institutions? That means this many reference standards, earlier we used to purchase from the other nations. Now, we can make our own product. Proudly, we can say that this is made in India. So time to time, we used to launch the products. You can go to our NPL website and you can see what are all the Indian reference material, that is indigenous standards are there. It is very cheap. So that's what I used to say. Our knowledge, we are not transforming into technology. We are not transforming into devices, because the bridging, the interface is not there. So we have to make the interface. So if it is there, then now we would have our own emails. Now we would have our own social platforms. That means these many startup industries, if n number of startup industries are there, then each and everyone will get the job. So this is the simplest mantra. So I will not take much time. So again, I am thanking my guru, Professor Johnson, and then all my faculty members of this great institution of St. Joseph's College. And again, I am saluting my great institute for giving the chance. Thank you very much. Sir, your mic is muted. I am not able to hear anything. Can you unmute your mic?
See, this is a time in which you can ask questions to Dr. Vijayan, who will be ready to give explanation about the problems that you are facing in the new era. Because Sir has given you the scenario of present conditions of our country, how the students will have to face these problems. So you can ask questions. If there is no question from any of the participants, it's clear that all the explanations given by Dr. Vijayan clear, so that you are able to understand completely. Thank you, Professor. Participants really enjoyed the learning, the current scenario in advancing instrument calibration and the importance of measuring BP of Indian standards. We have to develop our own technology, and we should go for exporting rather than importing. That idea you have given to participants. You have explained about the CSR sponsoring for various activities throughout our country, and also explained about the birth of existence of the National Physical Laboratory. And you have given three important mantras also: one nation, one time, waste into wealth, one nation, one charger. Definitely our participants will take these into consideration, because we have to develop the technology to overcome these problems that we are facing it. We, the researchers, invented the plastic. It really mean we have to develop some solution to prevent and developing the technology to eliminate this. Also, you have mentioned about the product of NPL, indelible ink, example you have given, and also the NMI and its service to the nation. You have mentioned so many things. Need of reference materials for the measurement that we have developed in our country, which really help the students to know, or the participants to know about how far we are moving towards to achieve all those things. So we are having our own substances, reference materials for various instruments. Your scintillating speech will definitely motivate the participants in developing our own technology for various problems that our country is facing recently. So thank you so much for your speech, sir. It definitely enlightened our participants and will help them to move towards the new technology to eradicate all those problems that we are facing in our country. Thank you so much, sir.
Thank you very much, sir. Thank you very much.
Hello, Vijay. How are you?
Yes, sir. Fine, sir.
Can I share your email ID and contact details with our students
Yes, sir. Yeah, sure.
so that they can contact you directly?
Definitely, sir. Yeah. In my presentation itself, I have given
Okay.
all details. Maybe I hope
Okay.
you are also having my emails.
Yes, sir.
Maybe they can take it from Google also.
If they come, I will also give them so
Yes.
that they can be in touch with you.
Thank you,
Please
sir. Yeah,
help
thank you
them
very
for further activities for project or research.
Definitely, sir. Definitely, sir.
Thank
Always.
you.
Thank you, sir.
I am proud to say that he is one of our illustrious alumnus of St. Joseph's College. Give you a big hand.
Thank you, sir. Thank you very much.
Thank you very much.
Thank you very
Welcome.
much.
See you.
Bye, sir. Bye.
Thank you.
Thank you, sir, for sharing your inspirational words about India's path to Vikshit Bharat. Also, we are really mesmerized by your vision to improve the standards of India. I also extend my gratitude to Professor Dominic for sharing this session. Thank you, sir.
Research is the formalized curiosity. It is poking and praying with purpose. With this, we conclude day one of ICAM 2025. Extend my gratitude to all the speakers, participants, and organizers for making this event a successful one. Now I request the student participants of oral presentation to present here, and paper presentation to move, poster presentation to move on the KP Joseph Hall after the tea break.
Ladies and gentlemen, please have your tea, and the notice has been put forward. Oral presentation, we hear offline participants and the others can go for a tea and come back if you like to view the posters. Please load your PowerPoints here, oral presentation participants. So come here, come to the dais. The posters are going on in the KP Joseph Hall. You can take a view of the posters. You can see many posters have been already put up, and you can get a gaze of all the posters. You can get an idea of what is going on inside the department and outside the department. Okay? Yes. Thank you so much. Have a good evening.
நீங்க பார்க்குற இந்த பேக்ரவுண்ட் ஒரு ஏஐ ஜென்ரேட்டட் விஷுவல்.
கொஞ்ச நேரத்துல முடிச்சிடலாம்.
Sir, shall I start?
Yeah. So you can present for about 6 minutes and we will ask questions. So participants, please note that you will be evaluated based on the work, novelty, presentation and viva. So based on that you will be evaluated. So first we start with abstract number OT03.
Okay, good afternoon, everyone. My work is on a first principle study of 2D silicon polymorph, large honeycomb dumbbell-shaped silicon for hydrogen storage applications. So the introduction covers this is my objective, to design and model 2D LHDS polymorph to compute the adsorption energy of hydrogen on LHDS polymorph, to evaluate and interpret the electronic properties of hydrogen adsorbed LHDS polymorph, to examine the current challenges and future perspectives of hydrogen storage technologies. So, hydrogen is a promising So, hydrogen is a promising clean energy carrier due to its high high density and zero carbon emission. So, it faces certain storage challenges like it need high pressure tanks and cryogenic methods. So, to replace this, advanced 2D materials, which is an alternative to hydrogen storage, it can be treated as an alternative to hydrogen storage. So, 2D materials is nothing but a single layer of atom with unique physical, chemical and electronic properties. Examples of 2D material include graphene, silicene, germanium, etc., which shows a direct band gap and it's ideal for hydrogen storage application. These are the application mentioned. So the computational details, the software used to analyze is Burai 1.3 GUI of Quantum Espresso. Here it basically works on density functional theory, in which n-body problem is converted into a single body problem, and the proceeding is carried out by solving Consham equations iteratively, so that total optimized energy can be obtained from this. The equation displayed here is the Consham equation, which is solved iteratively to obtain finally the total optimized energy here. Next, this is the computational setup. Exchange correlation function, PBE, a part of generalized gradient approximation, which is nothing but that electron density approximation. Next, the basis set is the Gaussian basis with plane wave formulation. Basis set is wave function representation. Here, Gaussian type orbital. Next, pseudo potential. Pseudo potential is to replace the Coulomb potential, which arises due to the nuclear interaction from electron. This is nothing but the effective ionic potential. Then these are the structural parameters for my structure LHDS. Then DFT specific parameters is nothing but the maximum kinetic energy and charge density cutoff. Smearing scheme is it smoothens the energy around the Fermi level. Then the type is Gaussian type orbitals. D-Gauss is the width of the Gaussian smearing type. Then K-point sampling is nothing but the Brillouin zone sampling. Here they mentioned the first two terms represent the density of the grid and the last term represents the vacuum region. Convergence criteria is the stable electronic configuration obtained. Then the iteration mentioned. These are some simulation conditions. So the methodology here is silicon polymorph LHDS preparation. The CIF file is given as an input to the Burai. Geometric optimization of the initial structure is carried out. Then the structure is converted into a supercell of 211. Again, geometric optimization is carried out. Then hydrogen adsorption is made on 3 different sites. The site is mentioned here. Adsorption energy is finally calculated. If the adsorption energy lies between the specified range, then we don't adopt metal decoration. If it doesn't lies, we adopt metal decoration to enhance hydrogen adsorption here. Next, we move on to study about the electronic properties, that is the band structure analysis finally. Here, Silicon polymorph is nothing but the different structural forms of silicon. So here my structure is LHDS, which is large honeycomb dumbbell shaped silicon. It's look like a dumbbell shape. So the significance of silicon polymorph include tunability, high carrier mobility, semiconductor properties, etc. Then this polymorphs include high surface area, low density and stability. So the results and discussion part, here we compare LHDS and supercell dimensions. So the Bravais lattice changes here since the atomic rearrangement of atom occurs due to the absorption of hydrogen here. So the Bravais lattice with respect to that Bravais lattice index changes with respect to the Bravais lattice. Then the unit cell volume depends on the number of atoms per cell. Then the number of electrons is obtained and number of quantum states. It's nothing but the comparison between the both the states. Next, the electronic properties, the band structure is analyzed here. 0 electron volt determines the Fermi level. Below the Fermi level, valence band is located, and above the Fermi level, conduction band is located here. So, band structure of LHDS, indirect band gap is observed as the valence band maxima and the conduction band minima doesn't lie on the same line. But in case of LHDS supercell, they both lie on same line, and direct band gap is observed here. So the band gap transition is identified. Then the band gap energy is calculated using that formula, and it is found to be 0.1 electron volt for LHDS and LHDS supercell 0.2 electron volt. Both band gap exists, so it possesses semiconductor nature here. X-axis represents the high symmetry K points and Y-axis represents the energy in electron volt here. So the hydrogen adsorption is done using this formula. The first term represents the hydrogen adsorbed supercell, and the second term represents the optimized, that is the minimum energy of the supercell, and the third term represents the optimized energy of that hydrogen. So here we observed hydrogen in 3 different sites, and we have found favorable site to be between SA bond. Since the range is closer to that specified range, if it doesn't lie, doesn't lie between that range, metal decoration will be carried out in this process. So our partial work is completed now. The LHDS was this supercell of LHDS was designed. Band structure calculation was done, and the transition in band gaps was identified as the favorable for H2. Adsorption was identified. SA bond was identified as the favorable position for adsorption. Further, our work will be carried out by adding more number of H2 molecules, and the optimized energy will be identified, or else we are planning to do with other supercell dimensions too, and we are going to obtain hydrogen, that is the optimized energy for hydrogen storage applications. Thank you.
What is the basic difference between a direct and an indirect band?
Sir, if we will speak here about that valence and conduction band, sir. So, if the valence and conduction band doesn't lie in the same line, that is the high symmetric K points doesn't coincide in the same line, it is referred as an indirect band gap, sir. But if it lies along the same line, it is referred as a direct band gap, sir.
So what is the consequence of that?
Sir, actually we have studied in our studies that direct band gap will give us favorable, it will be a favorable position for H2 adsorption. So this transition will help us to obtain our energy finally, which will be used for hydrogen storage applications.
Okay, so what is a plane wave, or how do you differentiate a plane wave and a Gaussian wave?
Yes, sir. Plane wave is that wave function representation in the form of plane wave. Gaussian wave is Gaussian, it represents the Gaussian type orbitals, sir. In plane waves, the representation with respect to the plane wave we speak here, sir, but our type is Gaussian type orbital here.
Okay, so Gaussian is primarily an atomic orbital, whereas plane waves are for lattice, crystal lattices.
Okay.
So it's almost a three-dimensional wave. Okay, fine, thank you.
Thank you, sir.
Good evening to one and all present here. I am Roshni, a research scholar from Karunya University. I am going to discuss about the synthesis property applications of gelatin methocryol gelma hydrogels. Contents. Introduction about gelma, structure of gelma, its general property, synthesis, microfabrication techniques, other components and its applications. Gelatin methocryol is generally known as gelma, is an attractive photocurable material, is made by chemical modification of gelatin with methacrylic anhydride. It was developed in 2000 by Van den Balke et al. And it is also known as photo-cross-linkable gelatin. It is widely used in biomedical applications because of its excellent biocompatibility and biodegradability, then its modability. It's able to form chemical gel with the water-soluble photoinitiator. It's Iracure and LAP. Then gelma has a excellent, is widely used in tissue engineering because of its biocompatibility. Then thermogelation to form the gel. It is used in other like drug delivery, then tissue regenerations as a carrier. It's a structure of gelma. Thus, the gelatin is added with the methacrylic anhydride. It's both are there is a chemical properties are changing that. Then it forms as a gelma. Afterward, the gelma is undergo for a photoinitiator with the irragure. There is a photo cross-linking is aqueous. Then gelma hydrogel is synthesized. It's the general properties of the gelma. There are 4 properties. 1, physical, chemical, biological, then mechanical. Physical properties, its swelling, porosity, viscosity, then water observations, etc. Mechanical, concentration, degree of methacrylation, degree of substitution, storage modulus. Then biological, its biocompatibility, biodegradability, bioprinting, moldability. Then chemical, hydrophilic, photocurable, tunable, then thermostable. Next. It's a synthesis of gelma. First of all, we have add the gelma with the PBS buffer. We have stirred for a few minutes, then add methacrylic anhydride for drop by drop by. After stir for 3 hours at constant level. Then afterwards fill the solution. Afterwards filter the solution. Then dialysis it for 5 to 7 days. Afterwards, the gelma hydrogel is ready. Then freeze this until we use. Next slide. It's a microfabrication exists. There are six types of microfabrications are here. One is photo printing. The gelma hydrogel is prepared by the photo processing by UV light, extreme exposure of UV light. That's range is 365 nanometer. We have seen that in the structure for the photo linking. Then micromolds, there is a mold for the hydrogel making. From that we have made the gelma hydrogel. Afterwards self-assemble. The gelma and the photo initiators are generally assembled in a pattern. Then it forms as a gelma hydrogel. After microfluids, it's also a layer by layer material. Then 3D printing, we have set the pattern in the 3D printer. Then it's print the hydrogels as a scaffolds. Then fabric and fabrications. It will print the hydrogels as how the textile are printing the designs, like that it prints the hydrogels. These are the other components which we add with the gelma. Gelma with PMA is used for the breast cancer cells. Then gelma with PHEMA is used for mimicking the structure of the cornea. Is copying from the cornea's functions. Then the gelma with PECMA is used for the tissue regeneration and wound healing. Gelma with aldehyde is used for tissue regenerations, 3D models and future implants. Gelma with aldehyde methacrylate is used for bioink in bioprinting. Then gelma with CNTs is used as a cardiac tissue engineering. Then spinal cord injury is used for spinal cord injury recovery. Biomedical applications is used as tissue engineering, drug delivery, biosensor, organ on a chip. Tissue engineering we have bone degenerations, skin regeneration, tendon regenerations, then cartilage degeneration, vascular regenerations. In skin regenerations, we use it as a scaffolds, and the long period non-healable wounds are healed by the gelma hydrogel by using on that. Then bone regenerations, we are able to grow the new bone on the injured part. After we use in drug delivery, it's controllable drug release systems. It releases the drug on the wounded or unhealable place. It is safer and more efficient for us than used in biosensor. Today, it is an analytical device used to analyze the chemical and biological component. Afterwards, used in organ on a chip. It's drug screening platform.
Can you proceed? Oh.
That's all.
So what experiments and results you have?
No, sir. Now only going to start my research, sir. I'm a We have chosen this topic, so I just present this thing. We didn't even plan how to synthesize anything. We didn't plan. Just we have planned the materials. So.
Okay, thank you.
Good evening, respected professors and everyone. Myself Janani RK from Sastra deemed to be University. So today I'm going to share a few words about the project I'm pursuing in my MSc second year. So it's synthesis and molarity driven characterization of nanoparticles with different molarity. The table of contents are objective, introduction, synthesis, film casting, characterization and conclusion. Okay, before seeing the objective, I believe that you all have attended the lecture given by Dr. Narayanasamy Vijayan. So he was talking about the plastic. So we are using plastic covers not only for packaging normal materials but also for food packaging. So everyone is buying food from hotels, you know, you will be getting in plastic covers. So with or without knowing, we are actually going towards a very bad thing that might cause cancer, etc. So what can be the alternative for that? That is my research about. So it's nothing but the biodegradable films. So these biodegradable films are designed to degrade naturally over time. So they minimize the environmental impact. At the same time, they pack the food, and it's for a long time, it's steady, but it also doesn't pollute the environment. It can degrade. So they are typically from renewable resources, like plant materials, and also they provide sustainability. So in the introduction part, I'll be introducing what is the biocomposite I'm using and also about the plasticizers, and also the polyvinyl alcohol is used by me. The biocomposite I'm using is corn husk. So everyone is eating corn. We know it is covered by this husk. So which is nothing but an agro waste which is found abundantly in the nature. So it's nothing but a waste, but I'm telling it's not a waste. We can use it for synthesis of biodegradable films. And also this fresh aloe vera gel acts as a plasticizer to reduce its stiffness and also to make it as a gel. And polyvinyl alcohol, everyone knows that it is a biodegradable component, and it is also an eco-friendly product. Okay, and next this for the synthesis part, I have taken the zinc acetate dihydrate as my precursor salt, and it was kept in a beaker in the magnetic stirrer in 400 RPM for about 40 minutes. And also the second component which I have taken is NaOH. NaOH was taken in the same format in a beaker, and it was stirred in the magnetic stirrer for about half an hour. And the second step, what I have done is mixing this zinc acetate dihydrate, so to get zinc oxide. So I believe that everyone knows that zinc oxide is it's a biodegradable thing, and it is also given as GRAS, generally recognized as safe by Food and Drug Administration, US. And the zinc oxide was obtained as a solution, and we kept it for aging. And after that, we could see that the water, this diagram, we could see that the water and the solution is separator. And after that, it was washed for 3 to 4 times in the centrifuge. And after washing it in the centrifuge tube, we dried it actually in a petri dish. And after the dried component, we scrapped it out and we gave it for calcination. And we obtained the calcinated powder, zinc oxide powder. That was our first nanoparticle. Next is the biocomposite. The biocomposite, what I have taken is the corn husk. This is the corn husk. It was dried in the shade of light, and also it was given NaOH treatment. It was given a NaOH treatment, and after giving the treatment, it was also taken for another a week dried, and we got fibrous thing. This is that fibrous thing. And next, we grinded it in a mixer, nothing but a home mixer, and we obtained the biocomposite powder. And the next part is the film casting. Okay, we have obtained the biocomposite powder, and the next one, what I have taken is the plasticizer is also aloe vera gel, which is also of great medicinal value. So this aloe vera gel, fresh aloe vera gel was obtained, and 1 gram of aloe vera gel was taken. And it was also kept in a magnetic stirrer for about half an hour in 350 RPM. And after that, PEVA solution was also prepared separately in the same way. And after that, we mixed up this biocomposite powder, then the aloe vera gel with this PVA component, and we obtained a solution. And the solution was also stirred for about 2 hours. With a elevated temperature, heat temperature 50 degrees Celsius. And also after this thing, we poured it in the mold and kept in the hot air oven for about 2 days. Not complete 2 days. It was just for 6 hours in both the days. And then we were amazed to get out the film. So we peeled out the film and we obtained the thin film. So everyone might be thinking that it is a form of plastic. No, it's not plastic, but it's an alternative which is biodegradable, which can be used for food packaging and everything else. We can replace plastic with these thing. So that was the film casting. And next we gave for characterization, SEM analysis. So we took different molarities of the same process, and what molarities I have chosen is the control film without any nanoparticle, then 0.3 molar film, 0.6 molar film, and then 0.9 molar film. The 4 films were given for characterization. The first was the SEM characterization, and the control film was obtained with some. It was not homogeneous actually, but when we added nanoparticles, we could see that it became homogeneous as we increased the molarity. So the reason is nothing but the nanoparticles filled out the spaces left out by the PVA, and it turned out to be homogeneous film. So you could see that the 0.9 molar film is very homogeneous, which is what we studied. And the next study we gave for is the dielectric constant. The dielectric constant was studied with the help of capacitance values. What we have inferred is the control film had a dielectric constant value of 14.944. And the second one, 0.3 molar film, 12.258, and the third one was 18.3, and the fourth one was 25.57. This was the dielectric constant's value. And the next one is zeta potential. Zeta potential and DLS study was made, and the zeta potential values were also inferred. This is that control film. This is 0.3 molar, this is 0.6 molar, and this is 0.9 molar. And the next was DLS value. DLS is nothing but dynamic light scattering characterization. So the particles can be mixed with distilled water. The particle study was done. So we mixed it with distilled water, and we could see that and this was the J0 is nothing but the biocomposite, 563.9 nanometers, and the next one was 0.3 molar film, and the next one was 0.6 molar, and the final one is 0.9 molars. And conclusion. So what I conclude is, as we know, this plastics or a dangerous thing, we not for us, for our future. So we could alternate use this biodegradable films in our day-to-day life. Let us make the change. A plastic-free world can be created, which is necessary. Okay, thank you. Thank you.
Okay, I have some questions. Oh, what is meant by biodegradable?
So biodegradable. So degradable is if after using, if we throw in the soil, it can degrade, sir. It can decompose in the soil.
Okay.
Yes.
So how did you conclude? Do you have any experimental evidence that this particular group of materials is biodegradable?
Yes, sir, we have the test, but I didn't yet to do. But we can take some cut up part of film, and we can take some soil in a pot, and we can insert them in. And for 2 weeks, if we see there will be a slight reduced weight of the film, sir.
Okay. What is the role of ZNO here? Because ZNO is it's a toxic material.
Sir, yes, sir, but I guess so. The Food and Drug Administration of US recognized this as ZNO as generally recognized as safe, GRAS grade they have given for this ZNO, sir. It is edible, but in a small amount.
Okay. Now, why you are using polyvinyl alcohol?
Sir,
and
pardon?
You are using PVA.
Yes, sir. Yes, sir.
But you say that it is replaceable of plastic. So what do you mean by plastic?
So plastic is a polymer. So PVA, polyvinyl alcohol, sir. So yes, sir. But its hydrophilicity is reduced by this ZNO nanoparticles, sir, because they are hydrophobic. So by ratio, we can say that it is eco-friendly.
Okay.
Yes.
Okay.
Thank you, sir.
Sir, shall I start? Good evening all. My project title is a first principle study of 2D silicon polymer for honeycomb dumbbell shape for hydrogen storage using material. Objective: first I need to design the 2D silicon model for and its supercell 211. After that, to evaluate the electronic properties of the 2D silicon and its supercell 211. After that, I compute the hydrogen absorption energy.
Introduction. Hydrogen is a clean and energy density fuel cell. It's used to renewable energy source for transportation and of the challenges of hydrogen is efficient and cost effective of its usage to barrier. After its advanced materials are 2D material used in silicon, graphene, etc. These features are in the tunable properties, etc. My structure is honeycomb dumbbell silicon structure. It's a dump-like shape. Its properties is a tunable properties for electronic and mechanical properties. Its application for it's used in hydrogen fuels and sensor for and other hydrogen-related purpose. Methodology I used here is step 1 to design the polymorph for HDS 211 and geometric optimize using Burai for relaxed calculation, and step 3 electronic properties obtained for band structure. Step 4 hydrogen absorption energy calculated for 3 different sites, and lastly finally favorable position for the metal decoration. Computational detail. Here I am using the software as Burai 1.3 GNU for the extent correlation function is PBE with GGA. Pseudo potential file here is ultra potential. The absorption energy calculation, I have used this formula to calculate my absorption energy for the hydrogen position. These are the result just now I have. This is the first structure is my HDS structure. After 211 this structure is reconstructed. The Bravis lattice is for HDS it's a